Hello there, and welcome once again to Science for Sleep, where curiosity drifts like a gentle tide and science offers a calm companion for the night. Tonight, our journey takes us toward one of the most destructive and mysterious possibilities in the universe. Not a black hole, though they'll certainly wander through our path, but something even stranger, a concept many have never heard of. Something that sounds almost like a whispered rumour at the edge of astrophysics, the grav star. A word that carries both weight and speculation, a balance between gravity and vacuum, destruction and stability, known only in theory, but powerful enough to challenge our understanding of what really lurks in the dark corners of the cosmos. Before we explore that shadowy frontier, let me ask you something simple. Something grounding. Where are you listening from right now? Are you curled up in bed, maybe with the glow of a lamp dimmed to its lowest? Or are you halfway across the world, with daylight still outside your window, while you search for calm in the rhythm of another voice? Perhaps the stars are actually above you as you listen, scattered across the night sky. Those same stars whose fates we'll be speaking about soon. Stars that live, burn, and collapse in ways that create the stage for either black holes or maybe something else entirely. And as we wander into this cosmic conversation, if you find it soothing or intriguing, if it brings a small moment of calm, I'd be grateful if you gave the video a like or perhaps subscribed. It helps this quiet corner of thought reach others who might also need a gentle space for drifting curiosity. Now, let's ease into the story, because the idea of the most destructive thing in the universe isn't something we can rush toward. It requires context. It requires us to build from what we know to the edge of what we don't. It requires us to start with gravity, the force that has guided every motion of matter since the first atoms formed, the invisible architect shaping galaxies, stars, planets, and perhaps the most fearsome objects we can imagine. And tonight, gravity is our quiet guide. Gravity has always been both familiar and strange. We live under its constant pull, feeling it every moment, yet its true nature only reveals itself when we look far beyond our everyday lives. A dropped object falls to the ground, and we don't think twice. But stretch the same principle across billions of light years, and you find entire galaxies rotating, clusters binding together, and stars collapsing inward when their own fires burn out. Gravity is relentless. It never stops pulling. It doesn't switch off when a star reaches the end of its life. Instead, it demands a final payment, a collapse inward, as if collecting the debt for all the energy that star once radiated into space. To reach graver stars, we need to understand that collapse. Imagine a star, not the size of our sun, but one far more massive, 10 times greater, maybe 20 or 30 times greater. These giants live fast and burn bright, fusing hydrogen into helium into heavier elements, building layer upon layer in their cores until they reach iron. And iron is the end of the line for fusion. It doesn't release energy when fused, it consumes it. At that moment, the star can no longer resist the inward pull of gravity with the outward pressure of radiation. The balance tips, gravity wins, the star collapses. That collapse can lead to several outcomes depending on the mass. A smaller star might become a white dwarf, a fading ember of what was once a blazing sun. A heavier one might compress into a neutron star, a city-sized sphere of neutrons so dense that a teaspoon of its matter would outweigh mountains. But the most massive collapses lead to black holes, regions of space-time where gravity is so extreme that nothing, not even light, can escape. At least that's the story as we usually tell it. But black holes come with problems. Not practical problems for us on Earth, of course, since they're distant and silent, but theoretical ones for physics. The equations that describe them predict a singularity at the centre, a point where density becomes infinite, where the known laws of physics simply stop working. To physicists, infinity is rarely comforting. It usually means the theory is incomplete. It suggests that our understanding has hit a wall, and that somewhere a deeper truth is waiting, and it's in that gap, in that discomfort with singularities, that alternative ideas begin to emerge. One of them is the grav star. The word itself is short for gravitational vacuum star, and it represents a possible way nature could avoid producing a singularity while still allowing for something nearly as extreme as a black hole. Instead of collapsing into an infinitely dense point, a grav star would be structured differently. At its centre, instead of singularity, lies a region dominated by vacuum energy, the same type of energy that cosmologists think drives the expansion of the universe itself. That vacuum is surrounded by a thin but unimaginably dense shell of matter, holding everything together. The result is an object that could mimic a black hole in many ways, from a distance looking almost identical. But deep inside, the physics would be different. No singularity, no true event horizon, just an exotic balance of quantum fields, gravity, and vacuum energy. And if such things exist, they could be contenders for the title of the most destructive structures in the universe, not because they necessarily destroy more than black holes, but because they challenge the very idea of what destruction even means. Of course, the grav star is still a theoretical construct. No telescope has confirmed one. No gravitational wave signature has shouted its existence. But in physics, the act of imagining is powerful. Sometimes a thought experiment eventually becomes an observation. Other times, it remains a curiosity that helps refine our theories, even if it doesn't manifest in the sky. Either way, gravastars are worth our attention, because in considering them, we face the deepest questions about gravity, energy, and the fate of matter itself. And so tonight, instead of trying to reach definite conclusions, we'll slowly move from the familiar into the strange, from gravity's everyday pull to the wild frontiers where graver stars might exist. We'll walk through the physics step by step, not rushing, not skipping over the foundation, because the most destructive thing in the universe isn't simply about spectacle. It's about understanding how far the laws of nature can be pushed before they break or bend into something new. Gravity is one of those things so constant in our lives that it fades into the background. You feel it every time you stand, walk, or stretch your hand to pick up a cup of tea, and yet it's also the same force that holds planets in orbit, binds galaxies together, and decides the fate of stars at the end of their lives. For something we experience so casually, its true scale is overwhelming. To understand why graver stars matter, and why they represent one of the strangest possibilities in physics, we first need to look closely at gravity itself, because without it, there would be no collapse, no black holes, and no need for alternatives. Gravity is the architect of everything we see, and it has been quietly at work since the first second of the universe. The story begins with mass. Every bit of matter has mass, and Einstein's theory of general relativity tells us that mass bends space-time around it, that bending is what we feel as gravity. You can think of space-time as a flexible fabric, though the image is just an analogy. A planet placed in that fabric curves it, and anything moving nearby naturally rolls toward the curve. On Earth, that means apples fall from trees, rivers flow downhill, and we stay grounded rather than drifting into the sky. On cosmic scales, that bending of space-time organizes entire systems. Stars form because clouds of gas feel their own gravity pulling inward. Planets circle stars because space-time around those stars is curved. Galaxies rotate because their mass bends space deeply enough to guide billions of stars in orbit. Even so, gravity is a paradoxical force. Compared to the other fundamental forces, it is incredibly weak. The pull of a small fridge magnet can overcome the gravity of the entire Earth acting on a paperclip. Electromagnetism and nuclear forces dominate at the scale of atoms, yet gravity has one special feature that makes it the ruler of the universe at large scales. It always attracts. There is no opposite charge of gravity that repels. Positive and negative charges cancel each other out in electromagnetism, but mass just adds to more mass. That means the influence of gravity builds endlessly as you scale up. It may be weak in isolation, but across billions of stars, its cumulative pull sculpts the largest structures in the cosmos. When you look at the night sky, every star you see is burning against the inward pull of gravity. Fusion inside the core produces energy, and that outward radiation pressure balances the star's tendency to collapse. But gravity never sleeps. It doesn't weaken over time. As long as there is mass, there is a pull inward, demanding balance. Eventually, a star exhausts its nuclear fuel. When that happens, the balance tips. Outward pressure fades, and gravity takes over, compressing the star with astonishing force. That compression is what leads to supernova, neutron stars, black holes, and perhaps graver stars. Gravity is both the creator of structure and the destroyer of stars. It's fascinating to think about how universal gravity is. On Earth, we measure it as acceleration, about 9.8 meters per second squared. Drop something, and it falls with that acceleration no matter its weight. A feather and a hammer fall at the same speed in a vacuum as astronauts famously demonstrated on the moon. But when we leave Earth's surface and look outward, the numbers change. Gravity weakens with distance, but it never completely disappears. Even in the outer solar system, far from the Sun, its gravity still keeps planets bound. Jupiter and Saturn orbit at huge distances, but they never drift away, because that invisible tether continues to hold them. The scale becomes even more dramatic when you move to galaxies. Our Milky Way contains more than 100 billion stars, and gravity is the reason they all remain in orbit rather than scattering into space. In fact, when astronomers measured how galaxies rotate, they discovered something puzzling. The stars at the edges were moving too fast to be held by the gravity of visible matter alone. This led to the idea of dark matter, an unseen mass that adds to gravity's pull. Whether or not dark matter has anything to do with graver stars, it shows just how far gravity's influence extends. We can't even explain the motion of galaxies without acknowledging its hidden strength. But for all its reach, gravity is also mysterious. Newton described it as a force acting at a distance, an invisible attraction between masses. Einstein redefined it as geometry, the curvature of spacetime itself. Both descriptions work in different ways, but neither fully explains its nature. Quantum theory, which governs the small scales of particles, has never been reconciled with gravity at the larger scales. This gap in our knowledge is one of the biggest puzzles in physics, and graver stars live right in the middle of that puzzle. They are a theoretical attempt to describe what happens when gravity pushes matter to extremes where neither general relativity nor quantum mechanics can comfortably explain the outcome. It helps to imagine how relentless gravity can be in the final moments of a star. Picture a core collapsing. The atoms squeeze so tightly that electrons and protons combine into neutrons. The density becomes unimaginable, a city-sized object containing more mass than our Sun. This is a neutron star, held up only by neutron degeneracy pressure, a quantum effect that resists further compression. But if the star is heavier still, even that quantum resistance is not enough. Gravity continues, crushing inward without mercy. According to traditional black hole theory, this process doesn't stop until a singularity forms. But singularities are mathematical warnings more than physical descriptions. They tell us that our equations break down. The infinities they predict are not physical measurements, but signs that something deeper is happening. This is where physicists start asking whether gravity really allows singularities, or if instead some new state of matter or energy forms in those conditions. Graver stars represent one answer. Instead of collapsing to a point, the star might undergo a kind of phase transition. The core becomes a bubble of vacuum energy, something that resists collapse through its negative pressure, while the outer layers stabilize into a thin shell of dense matter. In this way, gravity is still the architect, still the force driving collapse. But instead of creating an impossible singularity, it builds a new kind of structure, one that we don't yet know for sure exists, but that fits within the framework of general relativity and hints at the possibility of new physics. There is something deeply compelling about the thought that gravity, the same force that pulls a dropped cup to the floor, could also sculpt such an exotic object at the heart of the cosmos. Its relentlessness is what makes stars shine, what ends their lives, and what possibly gives rise to gravastars. We often think of destruction as an ending, but in physics, destruction is simply transformation under forces that never stop acting. Gravity isn't malicious. It isn't even intentional. It just does what it always does, pulling matter inward, curving space-time, guiding the dance of planets and galaxies. But given enough mass, enough pressure, and enough time, it doesn't just build worlds. It can also create the strangest and most destructive things in existence. The power of gravity is so immense that even light, which travels faster than anything else we know, can be bent by it. This bending is called gravitational lensing, and it lets astronomers see distant galaxies magnified and distorted by massive objects in between. The fact that light itself can be curved shows how deeply gravity shapes reality. And if light can be curved, trapped, and perhaps extinguished by black holes or gravastars, then we're dealing with a force that doesn't just structure the universe. It defines the limits of what we can observe. To put it into perspective, think about standing at the edge of a black hole. There's a boundary called the event horizon. Cross it, and not even light can escape. The pull of gravity is so overwhelming that every possible path leads inward. Gravastars may not have a true event horizon, but their shells would still represent an almost impenetrable boundary, a surface where physics itself is pushed to its limits. In both cases, gravity is the master builder, creating structures that test the very language we use to describe the universe. And yet, we live our daily lives under the same force, feeling only its gentlest expression. It holds us to the ground, times our steps, and defines our sense of up and down. There is a strange comfort in realizing that the same quiet pull you feel when lying down at night is also responsible for stars being born, galaxies being held together, and gravastars possibly forming in the aftermath of stellar collapse. The scale is different, but the force is the same. This duality, the ordinary and the extraordinary, is what makes gravity such a profound subject. It's always there, yet its extremes are almost beyond comprehension. And if gravastars do exist, then they are monuments to gravity's relentlessness. Not just objects of destruction, but reminders that even the smallest everyday pull has cosmic echoes. Stars are the actors on gravity's stage, and their lives are defined by the same pull we have just been talking about. They are born when clouds of gas collapse under their own weight. They live by burning fuel that pushes outward against that collapse, and they die when that balance is finally broken. To understand gravastars and why their existence is even considered, we have to take a slow walk through the story of stars, because their beginnings, their long Middle Ages, and their often violent ends are what give rise to the most exotic objects in the universe. Imagine a vast cloud of gas in space, made mostly of hydrogen, with a sprinkle of helium. It drifts quietly for millions of years, barely noticeable against the backdrop of the galaxy. But within that cloud, gravity is always at work, pulling atoms together, making them move slightly closer, slightly denser, slightly warmer. As density builds, pressure rises. Eventually pockets form where the collapse accelerates, and in those pockets, temperatures climb to the point where hydrogen atoms begin to fuse. Fusion is the process that defines a star. It is the moment when matter becomes luminous, when energy is released in such abundance that it shines across the void. For small stars, the process is gentle. They burn their fuel slowly, glowing steadily for billions of years. Our own sun is one of these stable stars, a middleweight in cosmic terms. But for massive stars, those 10 or 20 times the mass of the sun, the The story is far more intense. They live fast and bright, burning through their fuel with astonishing speed. While the Sun will last about 10 billion years, a massive star may only live for a few million before running out of energy. In cosmic time, that is the difference between a long, peaceful life and a brief, spectacular blaze. As a massive star burns, it builds layers in its core like an onion. First hydrogen fuses into helium, then helium into carbon, then carbon into heavier elements like oxygen, neon and silicon. Each stage requires higher temperatures and pressures, and each stage produces less energy compared to the last. Finally, the chain of fusion ends with iron. And iron is a problem, because fusing iron does not release energy. Instead, it consumes it. The star can no longer resist gravity with the push of outward radiation. At this point, the balance that has held for millions of years collapses in an instant. The core implodes, and the outer layers rush inward, only to rebound in one of the most powerful explosions in the universe, a supernova. For a short time, the dying star outshines its entire galaxy, releasing as much energy in seconds as the Sun will emit over its whole lifetime. These explosions are more than just destructive. They are creative, scattering heavy elements into space, seeding the cosmos with carbon, oxygen and iron, the building blocks of planets, and life. In a sense, everything around you, including your own body, was once inside a massive star that lived, burned, and died billions of years ago. But the fate of the core after a supernova is what interests us most. If the remaining mass is small enough, it compresses into a neutron star, where neutrons are packed so tightly that matter reaches densities beyond imagination. But if the mass is larger still, even the quantum pressure of neutrons cannot withstand gravity. The collapse continues. According to conventional physics, nothing stops it until a black hole forms, a region where space-time curves so deeply that escape is impossible, where matter is crushed into a singularity. Yet it is here, in these extreme deaths of stars, that the idea of gravastars enters the conversation. What if gravity does not create singularities? What if instead the collapse halts in a different state, forming something that looks like a black hole from the outside but is structured differently within? Gravastars would be born from the same stellar deaths that give us black holes, but they would replace the singularity with a bubble of vacuum energy wrapped in a thin, dense shell. It is still destruction, but it is destruction that points toward a different physics. To reach that possibility, we have to remember just how relentless stellar evolution is. From the moment a star forms, its life is a struggle between fusion pushing outward and gravity pulling inward. That tension defines every stage, from birth to death. When fusion is strong, the star is stable. When fusion fades, gravity wins. And for the most massive stars, there is no peaceful retirement. They cannot fade gently into white dwarfs or drift quietly into obscurity. They end in collapse, in explosions, and in the creation of objects so strange that we struggle to describe them. Massive stars also teach us about scale. Consider Betelgeuse, the red supergiant in Orion. It is hundreds of times larger than our Sun. If placed in the centre of our solar system, it would engulf the orbit of Jupiter. And yet, for all its size, it will not last much longer than a few million years. Its core is burning furiously, racing toward collapse. When it does, it may leave behind a neutron star or a black hole, and perhaps, if physics allows, something stranger. Another example is Eta Carinae, a massive unstable system that has already erupted in violent outbursts. Its future is almost certainly a catastrophic collapse. The universe is filled with such stars, ticking clocks waiting for their final acts, and each of them is a laboratory for gravity at its most extreme. In a way, the life of a star is a perfect metaphor for the universe itself. It begins in collapse, finds stability for a time, and ends in transformation. For stars, that transformation can mean scattering elements into space, or creating objects like neutron stars, black holes, and perhaps graver stars. For the universe, it may mean expansion, cooling, and one day an end we cannot yet fully describe. But the physics is the same. Energy resists collapse until it can't. Gravity always wins in the end. When thinking about destruction, it's easy to focus on explosions, on the bright flare of a supernova. But in reality, the true destruction happens quietly, deep inside the star, in the moment when the balance tips. The implosion of the core is silent, invisible to the outside world until the explosion follows. That hidden collapse is what gives rise to the strangest objects in the cosmos, and it is why we must take the deaths of massive stars seriously when thinking about graver stars. Without them, there would be no stage for these exotic structures to exist at all. The cycle of stellar life also reminds us that destruction is not an exception in the universe. It is the rule. Stars form, they shine, they collapse, and they transform. Galaxies collide, black holes merge, graver stars may or may not exist. But the constant thread is change, driven by gravity and energy. To understand the most destructive thing in the universe, we don't need to imagine something alien. We only need to watch a massive star live and die. That process itself is destructive on a scale far beyond anything we can imagine on Earth. Graver stars are simply one possible outcome of that relentless pattern. The death of a massive star does not end with the explosion itself. That brilliant flash, so bright it can outshine an entire galaxy, is just the visible part of the process. What happens afterward, in the core that remains once the outer layers have been blasted into space, is where some of the most extraordinary physics in the universe unfolds. It is here that collapse shapes exotic remnants, objects so strange that we often struggle to describe them in words that feel grounded in everyday reality. A supernova begins when the core of a star can no longer support itself. Iron builds up, fusion stalls, and gravity takes over. The collapse happens in fractions of a second. Atoms are crushed, electrons are forced into protons, and neutrons dominate the core. Temperatures soar to billions of degrees, densities to levels beyond imagination. In this moment, the star is undergoing one of the fastest and most violent transformations known. The outer layers slam inward, rebound and tear outward into space as a shockwave, creating the dazzling spectacle of a supernova. For us, watching from across the galaxy, the light from such an event may travel thousands or millions of years before reaching Earth. When it finally arrives, we see only the brief outward glow. What we do not see, at least not directly, is the fate of the collapsed core, and that fate depends almost entirely on mass. The universe has thresholds, lines that determine what forms after collapse, and the difference between one outcome and another can be as small as a fraction of a solar mass. If the core is relatively light, perhaps no more than about 1.5 times the mass of our Sun, the collapse halts with the formation of a white dwarf. These objects are supported by electron degeneracy pressure, a quantum effect that resists compression. White dwarfs are stable, though faint, glowing softly as they cool over billions of years. But for more massive cores, electron degeneracy pressure is not enough. Collapse continues until neutrons themselves provide the support. The result is a neutron star, an object only about 20 kilometers across, yet more massive than the Sun. Neutron stars are extraordinary in their own right. Their densities defy imagination. A teaspoon of neutron star matter would weigh billions of tons. Their magnetic fields can be trillions of times stronger than Earth's, producing beams of radiation that sweep across space like cosmic lighthouses. These beams are so regular that when astronomers first detected them in the 1960s, they briefly considered the possibility of signals from intelligent life. Neutron stars, or pulsars as they're often called, are strange, but they are stable. They represent one possible outcome of stellar collapse. Yet there is a limit. If the mass of the collapse core exceeds about 3 times the mass of the Sun, even neutron degeneracy pressure cannot hold it up. Gravity wins again. The collapse continues, unstoppable. According to classical general relativity, the result is a black hole. Space and time curve so sharply that beyond a certain radius, the event horizon, no path leads outward. Matter falls inward without return, light cannot escape, and at the very centre, theory predicts a singularity of infinite density. Black holes are the most famous outcome of massive collapse, and they dominate both scientific study and popular imagination. But black holes are not the only possibility. The prediction of a singularity raises questions. Physics, at least as we know it, should not allow infinities. When an equation produces one, it usually means something deeper is missing. This discomfort with singularities is part of what inspired alternative models. Could the collapse of a massive star lead to an exotic object that avoids the singularity, while still mimicking many of the properties of a black hole? Gravastars are one such possibility, but before them, other ideas were explored as well. There are concepts like quark stars, where matter is compressed beyond neutrons into their constituent quarks. Some theories suggest that quark matter could form a stable phase at extreme densities, creating an object denser than a neutron star but not yet a black hole. Others propose boson stars, built not from normal matter at all, but from hypothetical particles like scalar bosons. These exotic possibilities emerge from attempts to blend what we know of particle physics with what we observe in astrophysics. Gravastars belong to this same family of speculative objects, all born in the aftermath of collapse, all trying to describe what happens when gravity presses matter beyond the limits of current theory. To appreciate why these ideas are considered seriously, it helps to remember that collapse is not a gentle process. It is violent beyond measure. The gravitational potential energy released when a star collapses is so vast that only a small fraction of it needs to be converted into radiation for a supernova to outshine its galaxy. Neutrinos, nearly massless particles, stream out in unimaginable numbers, carrying away most of the energy. For a brief moment, the collapsing core is a furnace producing more neutrinos than the rest of the universe combined. These signals are hard to detect, but they are the fingerprints of collapse. What remains afterward is the true question. Astronomers can measure the light from the explosion, but they must infer the identity of the remnant. Sometimes they find neutron stars, spinning rapidly and emitting pulses. Sometimes they detect black holes, revealed by the behaviour of surrounding matter or gravitational waves from mergers. But gravastars, if they exist, would be more difficult to identify. From a distance, they could mimic black holes almost perfectly, radiating little light, influencing their surroundings with similar gravitational fields. The difference would lie in their internal structure, in the fact that they would not harbour a singularity but instead a vacuum bubble surrounded by a thin shell of matter. This idea comes from the notion of phase transitions in physics. Just as water can exist as ice, liquid or vapour depending on conditions, matter under extreme pressures and temperatures may undergo transformations into entirely new states. Collapse may not lead directly to a singularity, but instead to a shift in the nature of space itself, producing vacuum energy in the core. That vacuum would exert negative pressure, resisting further collapse, while the shell provides the structure. The result is not a black hole, but something that behaves very much like one from the outside. The universe has likely produced countless such remnants since the first generation of stars. Each massive star that lived and died left behind something: a white dwarf, a neutron star, a black hole, or perhaps an exotic object like a gravastar. The challenge is distinguishing them, because from light years away, many of these objects appear similar. It is only by studying their gravitational effects, their collisions, and the signals they emit that astronomers hope to tell them apart. The birth of exotic objects in collapse is not just a matter of astrophysics. It is also a laboratory for fundamental physics. These remnants push general relativity and quantum mechanics to their limits, forcing them to confront each other in regimes neither was designed to handle alone. Graver stars, quark stars, boson stars, all these ideas arise because collapse is nature's way of asking us to reconcile the deepest theories we have. The deaths of stars are not just cosmic events, they're experiments written across the fabric of space-time, experiments that might hold the clues to unifying our understanding of the universe. It's humbling to realize that the process that produces such mysteries begins with something as simple as hydrogen, the lightest element, fusing into helium. That simple reaction powers the star's life, and when it runs out, gravity takes over. From that inevitability comes everything from gold in jewellery to the possibility of graver stars lurking in distant galaxies. The life and death of stars are not just cycles of creation and destruction, they are the foundation on which all cosmic complexity rests. When we ask what the most destructive thing in the universe might be, we are really asking about the endpoint of collapse. We are asking how far gravity can push matter and energy, and what forms when nothing is left to resist it. Black holes are one answer. Graver stars could be another. Either way, the process begins the same way, with a star that lived its life, exhausted its fuel and collapsed. The exotic objects born in those collapses are the universe's way of showing us what happens when physics is pushed to extremes. The supernova is not the end, but the beginning of something new. The quiet remnant left behind, dense beyond comprehension, is where the real story begins. These objects may look like shadows in space, invisible except for their effects, but they are also the laboratories of the cosmos. To understand graver stars, to even ask whether they exist, we must first appreciate that every collapse is both a destruction and a creation. Out of the death of a star comes the birth of something exotic, something that challenges the very theories we use to describe reality. When most people think about the most destructive things in the universe, the image that comes to mind first is almost always the black hole. They are the archetype of cosmic monsters, the silent engines of gravity that swallow anything that dares to come too close. Even though they are invisible by nature, the idea of them has spread far beyond physics textbooks into popular imagination. They have become symbols of mystery, danger, and fascination, and for good reason. To understand graver stars, we need to understand why black holes hold such a grip on our minds, and more importantly, what physics says about them. A black hole begins simply, with collapse. A massive star reaches the end of its life, its core can no longer resist gravity, and the collapse continues until something extraordinary forms. Instead of leaving behind a dense but stable neutron star, the mass is great enough that nothing halts the inward crush. According to general relativity, space and time themselves are pulled inward so steeply that they fold into a region from which no escape is possible. This boundary is what we call the event horizon. The event horizon is not a physical surface you could touch. It is not made of matter or particles. It is a boundary in space-time, a mathematical surface marking the point of no return. If you cross it, every possible path you could take, even those at the speed of light, leads inward. Nothing you do could prevent that. You are trapped, not because of a wall or a barrier, but because of the geometry of space-time itself. The event horizon is perhaps one of the strangest concepts in all of science, because it represents not a physical edge but a limit defined by the structure of the universe. From a distance, black holes are surprisingly simple. They can be described with just 3 numbers: mass, charge, and spin. This is sometimes called the no-hair theorem, the idea that black holes have no distinguishing features beyond these basic quantities. 2 black holes of the same mass, spin, and charge are indistinguishable, no matter what kinds of stars collapsed to form them or what kind of matter fell into them afterward. This simplicity is elegant, but it also strips away the individuality we might expect. Stars are unique, galaxies are unique, but black holes reduced to a few parameters. That very lack of features makes them powerful tools for physics, but also frustrating mysteries because they reveal nothing about what's happening inside. The event horizon itself raises deep questions. Imagine an astronaut falling toward a black hole. From their perspective, they cross the horizon without noticing anything unusual at that exact moment. Locally, the laws of physics still apply, and they feel no sudden change. But from the perspective of a distant observer, the astronaut never appears to cross the horizon. Instead, they seem to slow down, their signals stretch to longer and longer wavelengths, fading into invisibility as time appears to stop. This difference in perspective shows how strange relativity becomes near such extreme objects. Both views are correct in their own frames, yet they paint very different pictures of the same event. The idea of an event horizon also challenges us in more subtle ways. If information falls into a black hole, what happens to it? According to classical general relativity, it is lost forever. The matter is gone, the information about it erased beyond the horizon. But according to quantum mechanics, information cannot be destroyed. The tension between these views is what physicists call the black hole information paradox. Entire fields of research have been devoted to resolving this paradox because it represents a clash between the two pillars of modern physics. Graver stars, as an alternative to black holes, attempt to sidestep this paradox by offering an object that mimics many black hole properties but lacks a true horizon and singularity. But before we can consider them seriously, we have to sit with the strangeness of black holes themselves. Black holes are not just theoretical, we have evidence for them. Stars orbiting invisible companions, matter falling inward and heating up into bright X-rays, and most dramatically, the detection of gravitational waves from black hole mergers. In 2015, the LIGO Observatory recorded the ripples of spacetime from two black holes colliding, proving beyond doubt that these objects exist. Later, the Event Horizon Telescope gave us the first image of the black hole's shadow, the dark silhouette in the glowing disk of matter swirling around it. These observations confirm that black holes are real parts of the cosmos, not just abstract solutions to Einstein's equations. Still, even with this evidence, the nature of the event horizon remains elusive. We cannot peer inside, we cannot send signals across it. We can only observe what happens outside, in the hot plasma circling just above the horizon, or in the gravitational waves released when black holes merge. This limitation makes black holes both compelling and frustrating. They are real, but their most defining feature is that we cannot directly see or test what happens beyond their boundary. The destructive power of black holes is easy to imagine. Any object that passes too close can be torn apart by tidal forces, stretched into long strands in a process often called spaghettification. Entire stars can be shredded, their material forming disks that shine brighter than galaxies as they spiral inward. The energy released in these events is staggering, far beyond anything human technology could dream of producing. Yet at the same time, black holes are quiet. If nothing is falling in, they emit almost no light. They can sit in space, invisible, detectable only by their gravity. This duality, silent and invisible most of the time, yet capable of dramatic violence when matter comes too near, adds to their aura of menace. But black holes are not only destructive, they also play creative roles. Supermassive black holes, millions or billions of times the mass of the Sun, sit at the centres of galaxies. Their influence shapes the formation of stars, regulates galactic growth, and powers quasars, the brightest objects in the universe. Without black holes, galaxies might not look as they do, and the history of the cosmos could have unfolded very differently. In this way, black holes are not just monsters, they are architects as well, balancing destruction with creation. When we compare black holes to grav stars, the event horizon becomes the critical distinction. A grav star would not have a true horizon, but instead a thin shell of matter just outside where the horizon would be. This shell could prevent complete loss of information, avoiding the paradoxes that plague black hole physics. From far away, the difference might be undetectable. The gravitational pull would be nearly identical. The shadow cast against surrounding light might look the same. Only very precise measurements, perhaps of gravitational waves or subtle timing of light, might reveal the distinction. This is why grav stars remain speculative. They are difficult to rule out, because from the outside they are almost indistinguishable from the black holes we already observe. Still, understanding black holes and their horizons is essential, because they set the stage for why alternatives like grav stars are even considered. The singularity at the centre and the paradoxes of the horizon push physicists to ask whether there is another way. Black holes may be the most famous exotic objects in the universe, but they may not be the last word in collapse. And so, as we move deeper into this journey, we carry with us the image of a black hole, silent and invisible, defined by its horizon. A place where time and space themselves bend to a point beyond comprehension. When we talk about black holes, we often focus on the event horizon, because that is the boundary we can at least describe, even if we cannot cross it. But at the very heart of the black hole lies something far stranger, something that even the most confident physicists speak about with unease. That something is the singularity. It is the point where our equations predict infinite density, infinite curvature of space-time, and the complete breakdown of the laws we rely on to describe the universe. The idea of a singularity is not new. It emerges directly from Einstein's general relativity. When matter collapses under its own gravity with nothing to stop it, the solution to the equation suggests that all of the mass compresses to a single point, a region with no volume and infinite density. At that point, space-time itself becomes undefined. In other words, the very stage on which physics plays no longer exists in a way we can describe. The rules we use to explain everything from falling apples to the motion of galaxies simply fail. Infinity is usually a red flag in physics. It is not that infinity is always meaningless. In mathematics, it can be handled with care. But in physical theories, infinities usually indicate that the model has been pushed beyond its valid range. When a calculation produces infinity, it is the universe's way of telling us that we need a new description, a deeper framework. The singularity at the centre of a black hole is exactly that. It is not so much a real place we expect to find, but a sign that our current understanding is incomplete. This problem has troubled physicists for decades. On the one hand, general relativity has been confirmed again and again. Its predictions about the bending of light, the expansion of the universe, the behaviour of clocks and gravitational fields, and even the waves produced by colliding black holes have all been observed with remarkable precision. It is one of the most successful theories in science. On the other hand, its prediction of singularity suggests that it cannot be the final word. It works everywhere except in the most extreme conditions, and that exception is too important to ignore. One of the reasons singularities are so troubling is that they erase predictability. Physics is built on the ability to describe how systems evolve over time. If you know the laws and the initial conditions, you can in principle calculate what happens next. But at a singularity, the equations lose their ability to predict. The future beyond that point is undefined. This is more than a mathematical inconvenience. It challenges the very purpose of physics, which is to provide a consistent description of the universe. Some physicists argue that singularities are not real physical objects, but simply artifacts of the equations. In this view, the collapse of a star does not truly end at an infinite point, but instead transitions into some new state of matter or energy that we do not yet understand. Others believe that quantum mechanics, the theory that governs the very small, must somehow intervene. Quantum effects may prevent true singularities from forming, but we do not yet have a full theory of quantum gravity to prove this. The singularity problem is not just an abstract debate. It connects directly to questions about the origin of the universe itself. The Big Bang, the beginning of space and time, is also described by a singularity in general relativity. Just as with black holes, the equations suggest infinite density and temperature at the very first moment, And just as with black holes, most physicists believe this indicates not a literal infinity, but a limitation of the theory. Whatever resolves the singularity inside black holes might also resolve the singularity at the beginning of the universe. That is why this problem is so central. It is not just about what happens deep inside collapsed stars, but about the foundations of cosmology itself. It is here that gravastars enter the picture. They are one proposal to avoid singularities altogether. By replacing the interior of a black hole with a region of vacuum energy, gravastars eliminate the point of infinite density. The collapse halts before reaching that mathematical abyss, and the structure stabilizes into something new. From the outside, the object still looks almost identical to a black hole, but inside the singularity has been avoided. In this way, gravastars attempt to solve the singularity problem by rewriting what happens during collapse. Other alternatives exist as well. Loop quantum gravity, a candidate theory for unifying general relativity with quantum mechanics, suggests that space-time itself has a discrete structure at the smallest scales. If this is true, then collapse might not continue infinitely, but instead bounce at a minimum size, creating a new phase instead of a singularity. Some string theory models propose similar mechanisms, where additional dimensions or exotic states of matter prevent the formation of true infinities. These ideas are still speculative, but they show how seriously the singularity problem is taken. Even without a complete theory, we can consider the physical consequences. If singularities truly exist, they are hidden from us by the event horizon. No information escapes, so perhaps it does not matter what lies inside. But this answer is unsatisfying, because the singularity is not just a hidden feature. It is a symptom of a deeper inconsistency. If our equations fail there, they might also fail in ways we have not yet discovered elsewhere. Ignoring the singularity problem risks leaving a gap in our understanding of reality. The idea of singularities also forces us to confront uncomfortable philosophical questions. If time and space themselves end at a singularity, what does that mean? Can we even speak of what lies inside if the very concepts of inside and time cease to exist? These questions blur the line between physics and philosophy, but they are inevitable when our theories reach their limits. They remind us that science is not only about what we know, but also about recognizing the boundaries of that knowledge. Some physicists are optimistic that future observations may help distinguish between singularities and alternatives. Gravitational waves, for example, carry information about the structure of the objects that produce them. If black holes truly have singularities, the signals might differ subtly from those produced by gravastars or other exotic remnants. Similarly, the way matter falls inward and the way light behaves near the horizon could reveal small differences. These are difficult measurements, but as our technology improves, we may one day be able to test them. Until then, the singularity remains both a warning and an opportunity. It is a warning that our best theory of gravity has limits, and that we must not take its predictions too literally at extremes. But it is also an opportunity, because resolving the singularity problem could lead to the next great leap in physics. Just as Einstein's relativity extended and refined Newton's laws, a future theory of quantum gravity may extend and refine Einstein's. In that refinement, the infinite densities may vanish, replaced by a new description of reality that makes sense where the old one failed. This is why the singularity problem matters so deeply. It is not a minor flaw at the edge of an otherwise perfect theory. It is a central challenge that connects the smaller scales of quantum mechanics with the larger scales of cosmology. It is a reminder that even our most powerful ideas are provisional, subject to revision when they meet the full complexity of the universe. And in that sense, singularities are not just problems, they are signposts pointing the way toward new physics. Once physicists realized that singularities were not just mathematical curiosities but unavoidable consequences of general relativity under collapse, the need for alternatives became urgent. A theory that works beautifully in so many ways but fails catastrophically in its most extreme predictions, invites us to look deeper. The question is not whether black holes exist. We have overwhelming evidence that they do, but whether the description of their interiors as singularities is complete. If it isn't, then perhaps something else is happening in those places where gravity becomes overwhelming. That something else could be the key to uniting the different pieces of physics into a more consistent whole. The search for alternatives began almost as soon as Einstein's equations were written down. In the early 20th century, solutions to the field equations revealed the possibility of collapse and singularities, but even Einstein himself was skeptical that nature would allow such extremes. Over time, as more evidence for compact objects emerged, the skepticism shifted from whether collapse could happen at all to what exactly collapse produced. Was it really a singularity, or was that only a placeholder for new physics? Neutron stars were the first alternative revealed by observation. When astronomers discovered pulsars in the 1960s, they were seeing evidence of objects so dense that no one had imagined them before. These city-sized remnants, held up by neutron degeneracy pressure, were once thought impossible, yet there they were, beaming radio waves across the cosmos. Their discovery reminded physicists to stay humble. What once seemed unimaginable could turn out to be real. That lesson drives much of the modern search for alternatives. Beyond neutron stars, the imagination of physicists has produced a wide range of possibilities. Quark stars, for example, are hypothesized to form when the pressure inside a collapsing core becomes so extreme that neutrons themselves break down into their constituent quarks. Instead of a ball of neutrons, the star becomes a ball of quark matter. Some even suggest that such objects could be made of strange quarks, forming so-called strange stars. These remain hypothetical, but they show that once you begin to consider collapse at the most extreme levels, many different forms of matter could emerge. Another idea is the boson star. Unlike ordinary matter, which is made of fermions, particles that obey the Pauli exclusion principle, bosons can pile together without exclusion. If certain kinds of bosons exist, such as the hypothetical scalar particles suggested by some theories, they could form stars that are very different from anything we've observed. Boson stars could be stable, massive, and nearly invisible, interacting only through gravity. They might even explain some aspects of dark matter. Then there are wormholes, speculative structures that emerge as solutions to Einstein's equations. Wormholes are not stars in the usual sense, but they represent another possible alternative to black holes. Instead of collapsing to a singularity, spacetime might pinch off into a tunnel connecting two regions of the universe. Whether such structures could exist stably is highly debated, but they remain a fascinating possibility. Amid these alternatives, gravastars stand out because they are designed specifically to address the singularity problem while remaining consistent with general relativity. Instead of a point of infinite density, a gravastar replaces the interior with a bubble of vacuum energy. That vacuum exerts a repulsive pressure, counteracting collapse, while a thin shell of matter forms around it. From the outside, the gravastar looks very much like a black hole, but internally it avoids the singularity. It is an elegant idea, blending what we know about gravity with what we suspect about vacuum energy. The search for alternatives is not just theoretical indulgence. It is motivated by real observations and real puzzles. For example, the information paradox challenges the idea of a true event horizon and singularity. If information is truly lost inside a black hole, that contradicts the principles of quantum mechanics. Alternatives like gravastars offer ways to resolve this paradox because they do not have a true horizon in the same sense. Information might still be recoverable, or at least not lost in the way black holes suggest. Another motivation comes from cosmology. The accelerated expansion of the universe is attributed to dark energy, which behaves like a vacuum energy with negative pressure. If such energy exists on cosmic scales, perhaps it also plays a role in the interiors of collapsed stars. Gravastars are built on this idea, using vacuum energy to stabilize the structure and prevent singularities. In this way, they connect two of the biggest mysteries in physics: the fate of collapsed stars and the nature of cosmic expansion. The challenge, of course, is evidence. Black holes have been observed through their effects on surrounding matter, their collisions detected by gravitational wave observatories, and their shadows imaged by the Event Horizon Telescope. Graver stars and other alternatives have not yet produced clear observational signatures that set them apart. From a distance, a graver star would be almost indistinguishable from a black hole. Only subtle differences in how they ring after collisions, or how light behaves near their surfaces, might reveal the truth. That makes testing these ideas extremely difficult, but not impossible. Physicists continue to refine their models, searching for predictions that can be tested. Some suggest that graver stars would produce echoes in gravitational waves, faint signals following the main merger waveforms detected by LIGO and Virgo. These echoes could arise from the absence of a true horizon. If such signals are found, they could provide a way to distinguish graver stars from black holes. Others look to electromagnetic signals, hoping that differences in how matter falls onto these objects could reveal their nature. These searches are ongoing, and while no definitive evidence has emerged, the effort reflects the seriousness with which alternatives are considered. The pursuit of alternatives also reflects something deeper about science itself. It shows that even our most successful theories are not beyond question. Black holes are not doubted as astrophysical objects, but their interiors challenge our understanding. Instead of accepting infinities, physicists ask what else might be possible. That willingness to question, to imagine, and to test is what keeps science alive. Graver stars may or may not exist, but the act of considering them sharpens our understanding of both relativity and quantum theory. It is easy to forget that black holes themselves were once speculative. For decades, they were considered curiosities of mathematics rather than real astrophysical objects. Only when evidence accumulated did they become accepted. Alternatives like graver stars occupy a similar place today. They may remain theoretical, or they may one day be confirmed as real. Either way, their study pushes the boundaries of our knowledge. As we drift deeper into this exploration, it becomes clear that the universe is not short on surprises. Each time we think we have reached the edge of understanding, new puzzles emerge. The singularity problem, the information paradox, the mystery of dark energy. All of these point toward physics we do not yet grasp. Alternatives to black holes like graver stars are stepping stones on the path to that deeper knowledge. They may not be the final answer, but they help guide us forward. Telescopes scan the skies, detectors listen for ripples in space-time, and theorists work through equations, all in pursuit of a clearer picture. Whether black holes hide singularities or are replaced by something more subtle, the answer will reshape our understanding of gravity, energy, and the structure of the universe. For now, we hold the possibilities in our minds, knowing that the truth may be stranger than any one idea, and that the act of searching is itself part of the journey. The graver star is one of those ideas in physics that sounds almost like science fiction at first encounter, a word that feels as though it belongs in a novel or a film rather than a serious scientific journal. Yet behind the unusual name lies a careful attempt to answer some of the most difficult questions raised by black holes, to understand why physicists propose graver stars and why they continue to consider them even in the absence of direct evidence. We have to look closely at the structure they suggest and the reasoning behind it. The term graver star is short for gravitational vacuum star. The name itself captures the essence of the idea. It is a star-like object, formed from gravitational collapse, but instead of collapsing all the way to a singularity, it halts in a very different state. At the heart of this object lies not ordinary matter, not even neutrons or quarks, but vacuum energy. This vacuum energy is the same concept that appears in cosmology to explain dark energy, the mysterious force driving the accelerated expansion of the universe. In the graver star model, vacuum energy fills the interior, creating a repulsive pressure that counters the pull of gravity. Surrounding this vacuum core is a thin but incredibly dense shell of ordinary matter, compressed to near unimaginable levels. The shell is the anchor of the structure, holding the vacuum region in place and defining the object's boundary. Beyond that shell, space-time looks almost identical to that around a black hole. To a distant observer, the Grav star's gravitational field would be indistinguishable from that of a black hole of the same mass. Light bending, orbital dynamics, and even the shadow against surrounding gas would all appear similar. The key difference lies in the absence of an event horizon and a singularity. In the traditional black hole model, collapse proceeds until an event horizon forms, enclosing a singularity at the centre. In the Gravastar model, the collapse undergoes a phase transition before this point. Instead of a singularity, the vacuum core forms, and instead of an event horizon, the shell becomes the defining edge. Matter does not vanish into an inaccessible region beyond time and space. Instead, it encounters the shell, a physical surface that prevents total disappearance. This structure was proposed in the early 2000s by Powell Mazur and Emil Motola, who sought to resolve the contradictions that black holes presented. Their idea was that space-time itself could undergo a kind of phase change under extreme conditions, much like water freezing into ice or boiling into vapour. At the densities and pressures reached during collapse, space-time could shift into a new state, producing vacuum energy that resists further compression. The Grav star is the astrophysical result of that transition. The physics behind this concept is tied to our understanding of vacuum energy. In quantum field theory, even empty space is not truly empty. It seethes with fluctuations, particles and antiparticles, appearing and vanishing in fleeting moments. This vacuum energy has measurable effects. The Casimir effect, for instance, demonstrates that vacuum fluctuations can exert a force between closely spaced plates. On cosmic scales, vacuum energy is believed to drive the accelerated expansion of the universe. If vacuum energy can push the universe apart, perhaps it can also hold up the core of a collapsed star, balancing gravity in a way that avoids singularities. The shell in the Grav star model is equally important. It must be incredibly dense, perhaps formed of exotic states of matter we do not yet fully understand. Its role is to separate the vacuum core from the external space-time, maintaining the stability of the structure. Without the shell, the vacuum would expand outward uncontrollably, or the core would collapse inward. With it, the system reaches equilibrium. The thickness of the shell is tiny compared to the overall size of the object, yet it carries enormous density and strength. One of the most fascinating aspects of Grav stars is how closely they mimic black holes from the outside. If you were orbiting such an object, measuring its mass and gravitational pull, you would see no difference from a black hole. If you watched light bend around it or measured the dynamics of a nearby star, the results would be the same. Even the shadow that appears when hot gas swirls around would look nearly identical. This mimicry is part of what makes Grav stars difficult to rule out. They hide in plain sight, potentially masquerading as the very black holes we think we have already observed. The differences would emerge only in the details. For instance, when two of these objects merge, the gravitational waves they produce might differ subtly from those of black holes. Instead of the clean ringing pattern of a horizon absorbing all vibrations, there might be echoes, faint reverberations caused by the shell-reflecting waves. Detecting such echoes is difficult, but it is one of the ways physicists have proposed to test whether Grav stars exist. Similarly, the way matter interacts with the shell rather than disappearing past a horizon could produce different observational signatures, though again, detecting these would be challenging. Another reason Grav stars are intriguing is that they touch on deep connections between astrophysics and cosmology. If the same vacuum energy that drives cosmic acceleration also stabilizes collapsed stars, then these objects are a bridge between the larger scales of the universe and the smallest, most compact remnants of stellar death. They bring together questions about dark energy, quantum fluctuations, and gravitational collapse into one unified picture. Whether or not gravastars exist, the very act of considering them pushes us to think about how these domains are connected. It is important to emphasize that gravastars are not simply an ad hoc invention. They are motivated by real tensions in physics. The singularity problem, the information paradox, and the nature of vacuum energy all converge in this idea. The gravastar is one possible resolution, a model that allows collapse to continue without breaking the laws of physics. While it remains speculative, it serves as a testbed for exploring these questions. By working through the implications of gravastars, physicists gain insights that may apply even if the objects themselves do not exist. Some critics argue that gravastars are too contrived, that the precise conditions needed to form them make them unlikely. But others counter that black holes themselves once seemed unlikely, and that nature often surprises us with phenomena we had not anticipated. Pulsars, quasars, and gamma-ray bursts were all mysterious before they were understood. Gravastars might be another addition to that list, waiting to be revealed by future observations. From a broader perspective, the concept of gravastars reflects the creativity of science. Faced with a paradox, physicists imagine alternatives, test their consistency, and look for ways to connect them with observation. Whether gravastars are real or not, they are part of this process. They are a way of asking, what if the story of collapse is different from what we think? What if black holes are not the only outcome? What if vacuum energy plays a role in shaping stars as well as galaxies? These questions keep the search alive. The gravastar remains a theoretical construct, a possibility at the edges of our understanding. Its vacuum core and dense shell challenge us to think differently about what collapse produces. It is neither a neutron star nor a black hole, but something in between, something that shares features of both while avoiding their extremes. In that balance lies its fascination, because it shows us that the universe may not always choose the simplest path, but instead may reveal new states of matter and energy when pushed to its limits. The strange idea of gravastars really rests on one central ingredient, something that sounds abstract but is woven through modern physics at every level. That ingredient is vacuum energy. To appreciate why it matters, and why it plays such a crucial role in the concept of a gravastar, we need to spend some time understanding what vacuum energy actually is, how it connects to Einstein's cosmological constant, and why it might hold the key not only to collapsed stars but to the fate of the universe itself. In everyday language, a vacuum means emptiness, a region where there is nothing at all. If you pump the air out of a container, you might say you have created a vacuum. But physics teaches us that even the most perfect vacuum is not truly empty. Space itself is filled with quantum fields, invisible entities that span the entire universe. These fields never vanish completely. Even in the absence of particles, they fluctuate, bubbling with temporary excitations. Virtual particles appear and disappear in unimaginably short timescales, contributing tiny bursts of energy before vanishing again. What we call vacuum energy is the net effect of these fluctuations. This idea is not just speculation. Quantum field theory predicts it, and experiments confirm it. One of the most famous demonstrations is the Casimir effect. Place two metal plates very close together, with only a tiny gap between them. Because of quantum fluctuations, the vacuum energy between the plates differs slightly from that outside. This imbalance produces a measurable force that pushes the plates together. It is a small effect, but it is real, and it shows that the vacuum is not an inert nothingness. It has structure and energy, even when no particles are present. On the larger scales, vacuum energy becomes even more significant. In 1917, Einstein introduced the cosmological constant, a term in his equations of general relativity designed to allow a static universe. At the time, he believed the cosmos was unchanging, neither expanding nor contracting. The cosmological constant acted as a repulsive force, balancing gravity. Later, when the expansion of the universe was discovered by Edwin Hubble, Einstein abandoned the constant, calling it his greatest mistake. But decades later, the cosmological constant returned in a new form. Observations of distant supernovae in the 1990s revealed that the expansion of the universe is accelerating, not slowing down. Something is driving space to expand faster over time, and the simplest explanation is a form of vacuum energy, described mathematically as a cosmological constant. This discovery reshaped cosmology. It told us that most of the energy in the universe is not in stars, planets, or even dark matter, but in the vacuum itself. This mysterious component, often called dark energy, accounts for roughly 70% of the total energy density of the cosmos. It is uniform, invisible, and acts with negative pressure, pushing space apart. The same negative pressure that accelerates the expansion of the universe is also the property invoked in the gravastar model. In a gravastar, vacuum energy fills the interior, counteracting the collapse of matter and preventing the formation of a singularity. The connection between cosmology and gravastars is striking. On the one hand, vacuum energy shapes the fate of the entire universe, determining whether it expands forever or slows to a halt. On the other, it may shape the fate of individual stars collapsing under gravity. In both cases, the repulsive pressure of vacuum energy balances the pull of gravity, but on vastly different scales. This dual role highlights how deeply vacuum energy is woven into the fabric of physics. But vacuum energy also presents one of the great unsolved problems. Quantum field theory predicts an enormous amount of vacuum energy, far greater than what cosmology observes. The difference is staggering, something like 120 orders of magnitude. This is often described as the worst theoretical prediction in physics. Reconciling this mismatch remains one of the biggest challenges in science. Gravastars add another layer to this puzzle. If vacuum energy can stabilize a collapsed star, then perhaps we are missing something fundamental about how it operates at different scales. The gravastar model assumes that under extreme conditions, such as during collapse, spacetime undergoes a phase transition into a state dominated by vacuum energy. The cosmological constant, usually thought of as a global property of the universe, becomes locally realized inside the object. This is a bold idea, but it reflects the way physics often works. Concepts that apply on one scale can sometimes appear in surprising ways on another. Just as quantum mechanics, developed to explain atoms, eventually turned out to be essential for understanding stars, vacuum energy might play roles both cosmic and compact. The presence of vacuum energy inside a gravastar also changes how we think about destruction. In a black hole, collapse leads to infinite density and an event horizon from which nothing can return. In a gravastar, collapse leads to a vacuum bubble that resists further compression. The destructive pull of gravity is balanced by the equally strange repulsion of the vacuum. Instead of ending in singularity, the process stabilizes. Whether this stabilization is real or only theoretical remains to be seen, but it illustrates how vacuum energy can transform our understanding of extreme environments. Another way to think about this is in terms of pressure. Ordinary matter resists compression through positive pressure. As density increases, pressure increases, pushing outward. But vacuum energy is different. It has negative pressure, which means that instead of resisting expansion, it encourages it. This negative pressure is what drives the expansion of the universe, and in a gravastar it is what holds the core against collapse. The shell provides the containment, but the vacuum energy inside is what prevents singularity. The interplay between vacuum energy and gravity raises fascinating questions. Is the cosmological constant truly constant, the same everywhere and every when? Or can it vary in different conditions, such as inside a collapsed star? If it can vary, then gravastars may not be just theoretical curiosities. They could be natural outcomes of collapse, hidden in the same places where we already expect black holes. From the outside, we might never know the difference. From the inside, the story would be completely different. Physicists continue to debate the nature of vacuum energy. Is it a fundamental property of space-time itself, or an emergent effect of quantum fields? Does it remain constant across the history of the universe, or can it evolve over time? These questions matter not only for cosmology but for objects like grav stars. If vacuum energy can be localized and stabilized, it may explain how grav stars could exist. If not, then the idea may remain only a mathematical possibility. Still, even as debates continue, vacuum energy remains central to our models of the universe. Without it, we cannot explain the acceleration of cosmic expansion. With it, we face paradoxes and mismatches with theory, but we also gain a tool for connecting phenomena across scales. The cosmological constant is one of the simplest modifications to Einstein's equations, yet it opens doors to some of the deepest mysteries. In grav stars, it becomes not just a global property but a local one, shaping the fate of individual stars. It is remarkable to think that the same concept explaining the fate of the entire cosmos might also explain the structure of exotic stellar remnants. That dual role captures the unity of physics. The same laws and ideas that govern galaxies also govern particles, and sometimes the bridge between them is stranger than we could have imagined. Grav stars remind us that vacuum energy is not an abstract curiosity, but a potential actor in the drama of stellar collapse. The cosmological constant remains both a solution and a problem. It solves the mystery of accelerating expansion, but creates the mystery of its own magnitude. It provides a way to avoid singularities, but raises questions about how such a transition could occur in collapse. It is both the simplest and most puzzling idea in modern physics, and its role in grav stars is a perfect example of how the universe uses the same tools in ways we're only beginning to understand. If the vacuum core is the heart of a grav star, then the shell is its skin and skeleton, the structure that holds everything together and makes the entire concept viable. Without the shell, the vacuum energy inside would not remain contained. It might expand outward endlessly or collapse back in on itself. With the shell, however, the system finds a delicate balance, one that prevents singularity while still producing an object that, from the outside, looks very much like a black hole. Understanding this shell means thinking about matter under conditions so extreme that even neutron stars seem tame by comparison. The shell in the grav star model is not a thick layer, but an incredibly thin one, at least in proportion to the object's size. Imagine an object the size of a black hole, with a radius measured in kilometers if it is stellar in mass, or even larger if it is supermassive. The shell that defines the grav star would be only a tiny fraction of that radius in thickness, yet it would contain an enormous amount of mass and energy. Its density would be beyond anything we have encountered directly, rivaling or exceeding even the densities inside neutron stars. What could such a shell be made of? The answer is not clear, but physicists speculate that it would involve exotic states of matter. At densities beyond those in neutron stars, neutrons themselves may break down into quarks, producing quark matter. Some models suggest that quarks could rearrange into new configurations, perhaps forming what is called strange matter, involving strange quarks in addition to the usual up and down quarks. If this matter is stable, it could form the substance of the shell. Others imagine even more exotic possibilities, involving condensates of bosons or other quantum fields. The truth is that we do not yet know what matter does under such conditions, because no experiment on Earth can replicate them. Grav stars serve as theoretical laboratories for imagining these extremes. The role of the shell is to provide pressure, preventing the vacuum core from expanding and stabilizing the overall structure. The vacuum inside pushes outward with negative pressure, while gravity pulls everything inward. The shell sits between these opposing forces, maintaining equilibrium. In a sense, it is like the walls of a balloon. Air pushes outward, the material of the balloon holds it in, and the two together form a stable structure. But in the case of a grav star, the forces involved are not gentle. They are cosmic, involving energies and densities that defy human intuition. One of the fascinating aspects of the shell is its potential to act almost like a surface. In a black hole, there is no surface. Crossing the event horizon, There is no material boundary, only the point of no return in space-time. In a gravastar, by contrast, the shell is a physical entity. If matter falls inward, it does not vanish past a horizon. Instead, it collides with the shell. The question then becomes, what happens to that matter? Does it stick to the shell, adding to its mass? Does it get converted into new states of energy? Does it release radiation in the process? These are open questions, but they offer ways to distinguish gravastars from black holes observationally. If a gravastar has a surface, it might emit radiation differently than a black hole, wherein falling matter simply disappears. The physics of the shell also raises questions about stability. Can such a thin, dense layer remain intact over long periods? Would it collapse inward under its own weight, or be pushed outward by the vacuum inside? The balance is delicate, and much of the research into gravastars focuses on whether this balance is mathematically consistent. Early models suggest it could be, but the details depend on the properties of matter at extreme densities, which we do not yet fully understand. Another layer of complexity comes from rotation. Most astrophysical objects spin, and black holes are no exception. If gravastars exist, they too would likely rotate. How would rotation affect the shell? Would it bulge at the equator as planets do? Would it alter the stability of the vacuum core? Would it produce different signals in gravitational waves? These are questions that theorists continue to explore, because they may offer clues about how to tell gravastars apart from black holes in real observations. The thinness of the shell also connects to ideas about information. One of the puzzles with black holes is the information paradox. What happens to the information about matter that falls in? If black holes truly erase information, that violates quantum mechanics. If gravastars have a shell, perhaps the information is preserved there, encoded in its structure rather than lost beyond a horizon. This possibility makes gravastars attractive to some physicists, because it offers a way to reconcile gravity with quantum theory. The shell, then, is more than just a boundary. It is the key to the gravastar's identity. It is what allows the object to mimic a black hole from the outside while being fundamentally different inside. It is where matter and energy interact, where theory meets observation, and where the mysteries of vacuum energy and quantum fields converge. Without the shell, the gravastar would be nothing more than an unstable bubble. With it, it becomes a candidate for one of the strangest and most destructive things in the universe. There is also an aesthetic elegance in the idea. Black holes, with their event horizons and singularities, represent the extreme of simplicity, reducing everything to mass, spin, and charge. Gravastars, by contrast, represent a kind of complexity, a layered structure with vacuum energy and matter in balance. They are not simpler than black holes, but they may be more realistic if singularities cannot exist in nature. The shell embodies this complexity, serving as the mediator between two extremes. From a practical standpoint, if gravastars do exist, the shell would be the place to look for evidence. Observationally, it might produce faint emissions when struck by infalling matter. It might produce echoes in gravitational waves when the object is disturbed. It might affect the timing of signals near its surface. Each of these possibilities is a potential window into distinguishing gravastars from black holes. The challenge is that these signals are subtle, and our instruments are only just becoming sensitive enough to search for them. Thinking about the shell also brings us back to the larger theme of physics under extreme conditions. Every time we have pushed into new regimes of pressure, temperature, or density, we have discovered new states of matter. The early 20th century revealed quantum mechanics, when classical physics could not explain atomic spectra. The study of high-energy collisions revealed quarks and gluons. Perhaps the study of collapsed stars will reveal the matter of gravastar shells. If so, they will not only solve the singularity problem but also expand our understanding of matter itself. As we reflect on the shell of a gravastar, it is worth remembering that even the most exotic ideas in physics are grounded in the same laws that govern everything around us. The balance of forces, the behavior of matter, the interplay of pressure and energy, these are the same principles that describe stars, planets, and even everyday objects. The difference lies in the extremes. Gravastars take those principles to their limits, and the shell is the manifestation of that limit, a place where known physics meets the unknown. The shell remains in our mind as the defining feature of the gravastar, thin but unimaginably dense, fragile in appearance but strong enough to hold back infinity. It represents the boundary between collapse and stability, between destruction and survival. It is both the wall and the window, the place where theory may someday meet observation. Without it, the gravastar is just an idea. With it, it becomes a possibility, waiting in the shadows of the cosmos for us to find. The universe, at its core, is a constant negotiation between forces. Every structure we see, from planets and stars to galaxies and clusters, exists because competing influences reach some kind of equilibrium. Stars shine because the outward push of fusion matches the inward pull of gravity. Planets hold atmospheres because their gravity traps gases against the tendency to escape. Even galaxies remain bound because gravity overcomes the kinetic motion of their stars. Without these balances, the universe would look very different. Gravastars, if they exist, represent one of the most delicate and extreme examples of this cosmic negotiation. Their entire identity depends on a balance between pressure and gravity so precise that a slight deviation could mean collapse into a black hole or dispersal into expanding vacuum. To understand this balance, it helps to recall what gravity does in the first place. Gravity is relentless. It pulls everything inward, always attracting, never repelling. Left unchecked, gravity compresses matter until it reaches the densest possible state. In a black hole, the pull is so strong that it crushes matter to a singularity. In a gravastar, however, something resists this final step. That something is pressure, but not the familiar pressure of gas or plasma. Instead, it is the negative pressure of vacuum energy at the core and the structural pressure of the shell that contains it. The vacuum energy inside a gravastar exerts an outward push. Unlike normal matter, which resists compression by pushing back harder as it gets denser, vacuum energy is peculiar. It has a constant energy density regardless of volume, and its pressure is negative. This means that instead of collapsing, it tends to expand. In cosmology, this expansion shows up as the accelerating universe. In a gravastar, it shows up as a force counteracting the inward pull of gravity. The more gravity tries to compress, the more the vacuum pushes back. But vacuum energy alone would not form a stable object. Left to itself, it would expand outward endlessly, just as dark energy drives the expansion of the cosmos. To confine it, a boundary is needed, and that is the role of the shell. The shell provides a physical wall, holding the vacuum energy inside and resisting its expansion. At the same time, the shell is pulled inward by gravity, wanting to collapse. The outward push of the vacuum energy balances this inward pull, stabilizing the entire system. It is a cosmic tug-of-war, with the shell caught in the middle, holding everything in place. The equations describing this balance come from Einstein's general relativity. Solutions to these equations show that under certain conditions, the stress energy of vacuum energy can exactly counteract the curvature of spacetime caused by mass. The result is not collapse to a singularity, but a stable configuration. The shell, though thin, provides the necessary boundary conditions, allowing the vacuum to exist inside without exploding outward. It is a precise dance of geometry and energy, one that can only happen under the most extreme circumstances. The stability of this balance raises questions. How precise must the conditions be? If the vacuum energy is slightly too strong, the gravastar could blow apart. If it is too weak, collapse would continue to a black hole. The model suggests that once formed, the balance is self-sustaining. The shell adjusts to contain the vacuum, and the vacuum supports the shell. But the formation process itself may be rare. requiring just the right conditions during stellar collapse. This may explain why gravastars, if they exist, are not everywhere but instead only in select places where nature finds the path. Rotation complicates the balance further. Most real stars spin, and when they collapse, that spin carries over. A rotating gravastar would not be perfectly spherical but slightly flattened at the poles. The centrifugal force from rotation would counter gravity near the equator, altering the stress on the shell. Would the vacuum energy still stabilize under such conditions? The equation suggests that it might, but the balance would be more complex, involving both gravitational and rotational terms. This complexity could, in fact, provide observational signatures, as rotating gravastars might produce gravitational waves with slightly different patterns than black holes. One of the reasons physicists are interested in this balance is its connection to fundamental theories. In quantum field theory, vacuum energy appears naturally, but with magnitudes that seem unrealistic compared to cosmology. In gravastars, vacuum energy is localized, providing a place to test how it behaves under extreme curvature. The balance between pressure and gravity in a gravastar is not just about astrophysics. It is also about understanding how quantum fields and spacetime interact, something that could illuminate the path toward a theory of quantum gravity. The balance also ties directly into the question of information. In a black hole, information seems to vanish beyond the horizon. In a gravastar, with its shell acting as a boundary, the information may be stored or re-emitted. The shell could act like a ledger, recording the interactions of matter that falls in, while the vacuum energy stabilizes the structure. If this is true, then gravastars not only solve the singularity problem but also the information paradox. They preserve the predictability of physics by avoiding true loss of information. From an observational standpoint, this balance might leave subtle traces. When two gravastars merge, the interaction of their shells and vacuum cores could produce echoes in the gravitational wave signal. Unlike black holes, which absorb oscillations cleanly, gravastars might ring slightly differently, like bells with hollow centers. These differences would be faint, but with sensitive detectors they might become measurable. In this way, the balance between pressure and gravity in gravastars is not just a theoretical curiosity, but something that could potentially be tested. It is also worth noting that the idea of balance between pressure and gravity is not unique to gravastars. Stars themselves are balances. White dwarfs are balanced by electron degeneracy pressure, neutron stars by neutron degeneracy pressure. Gravastars are simply the next step in this sequence, where vacuum energy and ultra-dense matter provide the support. Each stage represents a new kind of physics, revealed only when the universe pushes matter to its limits. The elegance of gravastars lies in how they extend this pattern. Instead of allowing collapse to run unchecked to infinity, nature may find another balance point, one that we had not considered until recently. If this is true, then gravastars are not exotic exceptions but natural continuations of the same principle that governs all stars: gravity pulling inward, something else pushing outward, and stability achieved at the meeting point. The idea that destruction can lead to balance may feel counterintuitive, but it is a theme in physics. The collapse of a star is destructive, yet it creates neutron stars and black holes, which are stable in their own ways. Gravastars add another possibility, where destruction leads to a balance that avoids extremes. In this sense, they embody the paradox of the universe itself. Out of violent collapse can come stable structures, out of chaos can come order, and out of destruction can come new forms of existence. As we carry this image forward, the gravastar becomes less of an outlandish speculation and more of a natural extension of physics. It is an object defined by balance, one that shows us how the same principles apply across scales. Pressure and gravity, attraction and repulsion, collapse and resistance. These are the themes of the cosmos, repeated in different forms. Gravastars may be one of the most extreme examples, but they are still part of this universal story. For most of modern astrophysics, Black holes have been the standard picture of what happens when gravity wins completely. Their features are familiar, even if still mysterious. The event horizon, the singularity, the way they trap light and matter. Graver stars, in contrast, are still only proposals, sketched in theoretical work and imagined as alternatives that avoid the problems black holes present. To understand graver stars, it helps to place them side by side with black holes, to examine what makes them so similar on the outside yet so profoundly different on the inside. From a distant perspective, the two objects look almost identical. Both are extremely compact, with masses packed into regions just a few kilometers across for stellar mass cases, or millions of kilometers across for supermassive versions. Both bend light strongly, producing gravitational lensing that distorts the images of background stars. Both can anchor accretion disks, the swirling structures of hot gas that form when matter falls inward. Both can cast shadows, dark silhouettes in the bright glow of surrounding material. If you were orbiting one at a safe distance, the experience would be indistinguishable. The gravitational field outside a graver star is mathematically the same as that of a black hole with the same mass. The difference appears only when you approach the boundary. In a black hole, once you cross the event horizon, there is no return. The geometry of space-time itself is such that all paths lead inward, toward the singularity. There is no surface, no stopping point, only the relentless inward pull. In a graver star, by contrast, the event horizon does not exist. Instead, there is the shell, a thin but incredibly dense layer of matter. Infalling material does not vanish into an unreachable region, but collides with this shell. The interaction may release radiation or alter the structure, but it does not disappear beyond the reach of physics. This distinction is subtle observationally but enormous conceptually. Black holes challenge the foundations of physics with their singularities and the information paradox. Graver stars avoid both by replacing the horizon and singularity with a shell and vacuum core. They are consistent with general relativity in the exterior but diverge in the interior. From the outside, no test of gravitational pull can distinguish them. From the inside, they are radically different objects. Another point of comparison is how they handle information. In the black hole model, once matter crosses the horizon, its information is lost to the outside world. According to quantum mechanics, this cannot happen, leading to the paradox that has troubled physicists for decades. Many attempts have been made to resolve it, from holographic principles to firewall hypotheses, but the debate remains unsettled. Graver stars sidestep the issue by providing a physical surface. Information might be stored in the shell or re-emitted in radiation, preserving the laws of quantum mechanics. If graver stars are real, they would neatly solve the information problem without needing exotic fixes. Theoretical comparisons also extend to dynamics. When two black holes merge, the resulting gravitational waves have a characteristic pattern: a sharp rise as the holes spiral together, a peak at the collision, and a ring-down phase as the new black hole settles. Graver stars would produce a similar signal, but with possible differences. The absence of a true horizon means that some of the gravitational waves might reflect off the shell, creating echoes after the main event. These echoes would be faint, but they are one of the proposed observational signatures that could distinguish graver stars from black holes. So far, gravitational wave observatories have not confirmed such echoes, but the search continues. Radiation provides another area of comparison. When matter falls into a black hole, it heats up in the accretion disk and emits X-rays and other forms of light. Once past the horizon, the matter vanishes from view. In a graver star, infalling matter would hit the shell. Depending on how the shell interacts with it, this could produce bursts of radiation different from those expected from black holes. Some models suggest that graver stars would be slightly less efficient at swallowing matter, leaving faint but detectable differences in emissions. Observing these differences is difficult, because the processes are messy and many factors are involved, but they offer another possible test. The comparison also highlights how both models extend from the same principles but diverge at the extremes. Black holes are natural consequences of Einstein's equations if taken to their logical conclusion. Gravastars modify the story by inserting a phase transition to vacuum energy before collapse completes. Neither violates relativity in the external solution, but they disagree about what happens at the core. The choice between them depends on whether we accept singularities as real or insist that nature must avoid infinities. There is also a philosophical dimension to the comparison. Black holes represent finality, regions where space-time itself ends. They are absolute in their simplicity, only mass, charge, and spin matter. Gravastars represent continuity, objects that maintain structure and avoid absolute endings. They suggest that even in the most extreme conditions, physics remains consistent and information is preserved. Which vision is closer to reality is not yet known, but the contrast captures two different attitudes about the universe. In practice, astrophysicists treat black holes as the working model because they fit observations so well. The motion of stars near the centre of our galaxy, the shadows imaged by the Event Horizon Telescope, the gravitational waves from mergers, all match black hole predictions. Gravastars remain speculative because no observation has yet required them, but this does not mean they are ruled out. Because they mimic black holes so closely from the outside, distinguishing them requires precision measurements that are only now becoming possible. One could think of black holes and gravastars as two branches of the same story. Both begin with massive stars collapsing. Both produce compact objects with immense gravity. Both can anchor galaxies and shape cosmic evolution. The divergence comes at the very end of collapse. Do we accept a singularity hidden behind a horizon, or do we insist on a new state of matter and energy that prevents it? That is the fork in the road. Theoretical physics often thrives on such forks. It is not that one model must be discarded immediately, but that exploring both sharpens our understanding. By working out the consequences of gravastars, physicists test the limits of relativity and quantum theory. By comparing them to black holes, they identify exactly where the tension lies. Even if gravastars turn out not to exist, the exercise helps refine our models. And if they do exist, the implications would be profound, changing not only astrophysics but our entire view of gravity and space-time. One final point of comparison is thermodynamics. Black holes, through Hawking radiation, are predicted to emit tiny amounts of thermal radiation due to quantum effects near the horizon. This gives them a temperature and entropy, tying them into the laws of thermodynamics. Gravastars, with their shells and vacuum cores, might behave differently. They might radiate in ways that preserve information, or they might have different entropy values. Studying these differences could shed light on the deep connection between gravity, thermodynamics, and quantum mechanics. In the end, black holes and gravastars are not enemies but siblings, born from the same equations and the same cosmic processes. One is the standard model, the other a speculative alternative. Both teach us about the extremes of nature, where gravity bends space so deeply that ordinary intuition fails. Whether the universe contains only black holes, or both black holes and gravastars, the comparison between them sharpens our insight into how the cosmos works. The idea of a gravastar is compelling, but for any astrophysical object to move from the realm of speculation into the realm of reality, it has to do more than solve theoretical puzzles. It has to endure. The universe is full of unstable ideas, structures that might be possible for an instant in a computer model or in a set of equations, but that nature never allows to last. To ask whether gravastars could be real is to ask whether they can survive as stable objects under the relentless conditions of the cosmos. Stability is the bridge between mathematics and existence. Without it, gravastars would remain only a clever proposal. The stability of a gravastar comes down to the interplay of its two defining features, the vacuum core and the ultra-dense shell. The vacuum energy inside exerts negative pressure, pushing outward, while the shell resists, held in place by its own gravity. This delicate balance, in theory, can reach equilibrium. But the question is whether that equilibrium is stable against disturbances. Could a graver star maintain itself if struck by infalling matter, if it spins, or if it merges with another compact object? Could it hold together for millions or billions of years, the timescales over which we observe black holes? The first kind of stability to consider is structural. Imagine the shell of the graver star as a barrier containing the vacuum energy inside. If the vacuum pressure is slightly stronger than the gravitational hold of the shell, the object could expand, tearing the shell apart. If the vacuum pressure is slightly weaker, gravity could crush the shell inward, leading to further collapse. For stability, the forces must match precisely. The mathematics of general relativity allows for such a match, but the margins are narrow. The shell must be tuned to the vacuum it contains. Some critics argue that this tuning is too fine, that nature would rarely achieve it. Others counter that collapse processes in stars might naturally find this balance, just as neutron degeneracy pressure naturally stabilizes neutron stars. Another kind of stability involves rotation. Real stars almost always rotate, and when they collapse, they carry angular momentum into their remnants. A rotating graver star would not be a perfect sphere, but slightly flattened at the poles, with centrifugal forces complicating the balance. Could the vacuum and the shell still stabilize under these conditions? Models suggest they might, but the stresses would be greater. In fact, rotation might even help in some cases, spreading the load and preventing collapse. But it could also introduce instabilities that tear the shell or distort the vacuum region. The outcome depends on details we do not yet fully know, because the physics of matter at these densities remains uncertain. Then there is the question of perturbations. No object in space exists in isolation. Gravastars, if they exist, would be bombarded by particles, struck by radiation, and occasionally collide with other objects. Each disturbance would challenge the balance. Would the gravastar absorb the impact, adjusting slightly but remaining stable, or would a disturbance tip it into collapse or dispersal? Some models suggest that gravastars could absorb small perturbations, with the shell flexing to accommodate changes. But large disruptions, such as mergers, raise bigger questions. When two gravastars collide, do they form a larger gravastar, or does the balance fail, producing a black hole? This is where gravitational wave astronomy may eventually provide answers, because the signals from such mergers could reveal whether the outcomes differ from black hole collisions. Thermal stability is another issue. Black holes, according to Hawking's predictions, emit radiation very slowly, shrinking over immense timescales. Gravastars with their shells might radiate differently. If the shell emits too much energy, it could cool and lose stability. If it emits too little, the balance might be disrupted in another way. The details depend on the properties of the shell material, which remain speculative. If the shell is made of exotic matter with unusual thermal behavior, it might be able to maintain stability. But until we know more about such matter, the question remains open. Even with these uncertainties, it is important to remember that stability is a common theme in astrophysics. Stars themselves are balances between gravity and fusion, and they can remain stable for billions of years. White dwarfs and neutron stars are balances maintained by quantum degeneracy pressures, and they too persist. If nature can produce these balances, it may not be unreasonable to think that it could also produce the more exotic balance of a gravastar. The fact that stability requires precision does not necessarily rule them out. After all, the universe is vast and rare outcomes can still occur often enough to be significant. Stability also connects to the information paradox once more. If graver stars are stable, they could serve as repositories of information, storing it in their shells rather than losing it beyond horizons. But if they are unstable, collapsing eventually into black holes, then they might only delay the paradox rather than resolve it. This makes the question of their longevity crucial. If graver stars can last as long as black holes, billions of years or more, then they could play a real role in cosmic evolution. If they collapse quickly, they may remain only a transitional phase. From an observational perspective, stability influences what we might detect. If graver stars are unstable, they might produce transient signals, bursts of radiation as they collapse or disperse. If they are stable, they might appear indistinguishable from black holes over long timescales. This makes the search for subtle signals such as gravitational wave echoes or unusual radiation from accretion even more important. The absence of clear instabilities in observations of compact objects suggests that if graver stars exist, they must be at least somewhat stable. Otherwise, we would see evidence of their collapse. One way to think about stability is through analogy. Consider a soap bubble. From a distance, it looks delicate, yet it maintains its form as long as the balance of forces holds. A slight disturbance can make it pop, but in the right conditions it drifts stably for a time. Graver stars are like cosmic bubbles, maintained by a balance between outward vacuum pressure and inward gravity, contained by a thin but strong shell. The analogy highlights both the elegance and fragility of the idea. If nature has found a way to make such bubbles stable on cosmic scales, then graver stars could be as real as black holes. The debate about stability continues in theoretical work. Some researchers argue that instabilities inevitably arise in the shell, leading to collapse. Others argue that the equations allow for stable configurations that could last indefinitely. Without observational evidence, the question remains unresolved. What is clear is that stability is the key factor in determining whether graver stars are more than mathematical curiosities. The universe is harsh and unforgiving. Only objects that can withstand its challenges survive to be seen. If graver stars can last, then they could be widespread, hiding among the black holes we think we have already identified. Their stability would mean they play roles in galaxies, in mergers, and in the growth of structures across the cosmos. If they cannot last, then they may remain rare, fleeting, or non-existent. Either outcome teaches us something about physics. If stable graver stars exist, they show that vacuum energy and exotic matter can combine to resist collapse. If they do not, then we learn that nature prefers the simpler path of black holes, and that singularities, uncomfortable as they are, may be unavoidable. For now, we hold both possibilities. Graver stars may be stable monuments to balance, persisting as silent alternatives to black holes, or they may be fragile constructs, collapsing before we ever have the chance to see them. Until we can observe more clearly, stability remains the deciding factor, the question on which the reality of graver stars depends. If graver stars are to be taken seriously, they must be understood not as fantasies outside the laws of physics, but as structures that emerge within the same framework that gave us black holes in the first place. That framework is general relativity, Einstein's theory of gravity. It is the theory that replaced Newton's picture of force with the idea of space-time curvature, and it is the theory that predicts black holes as inevitable consequences of collapse. For graver stars to exist, they must not violate general relativity outright, but instead reinterpret what the equations mean under the most extreme conditions. General relativity is one of the most successful theories in science. It has been tested again and again, from the bending of light around the sun during eclipses to the detection of gravitational waves a century after Einstein predicted them. Its mathematics is elegant, describing how matter and energy tell space-time how to curve, and how curvature tells matter how to move. In most cases, it works beautifully. The orbits of planets, the motion of galaxies, the expansion of the universe, all can be described with extraordinary precision. But general relativity is also unforgiving. It allows solutions that push reality to its limits, and one of those solutions is the singularity. The equations show that if matter collapses beyond a certain density, curvature becomes infinite, and space-time breaks down. Black holes are the natural outcome. For decades, physicists have debated whether these singularities are true physical entities or signs that the theory is incomplete. Graver stars enter this debate not by rejecting relativity, but by exploring a different solution within it. In the original Gravestar proposal, the equations of general relativity are used with a specific choice of stress-energy distribution. Instead of ordinary matter throughout, the interior is modelled as vacuum energy, which has a particular equation of state. In relativity, the equation of state describes the relationship between pressure and density. For vacuum energy, the pressure is negative and equal in magnitude to the energy density. This unusual property changes how space-time behaves. Instead of curving inward without limit, the negative pressure balances gravity, preventing singularity. The surrounding shell provides the boundary conditions that make the solution stable. This shows that gravastars are not fantasies imposed from outside. They are legitimate solutions to Einstein's equations, just as black holes are. The difference lies in the assumptions about what happens to matter under collapse. Black holes assume that matter continues inward until it reaches infinite density. Gravastars assume that at some point, matter undergoes a phase transition into vacuum energy, altering the equation of state. Both fit within relativity, but they lead to different outcomes. The beauty of relativity is that it is flexible enough to allow both possibilities. The field equations are not prescriptive about the type of matter or energy present. They describe how space-time responds to whatever is there. Change the stress-energy content, and you change the solution. This flexibility is both a strength and a challenge. It allows creative models like gravastars, but it also means that without observational input, we cannot know which solution nature chooses. One of the criticisms of gravastars is that they require exotic matter with properties we have not observed directly. But relativity does not forbid such matter. In fact, the theory itself makes no restrictions beyond requiring consistency with energy conditions, and even those conditions may break down under extreme circumstances. If vacuum energy exists on cosmological scales, as we believe it does in the form of dark energy, then it is not unreasonable to consider it inside collapsed objects. Gravastars extend this logic to the interiors of stars. There is also a historical precedent in relativity for considering exotic solutions. Wormholes, for example, are allowed by the equations, though their stability is questionable. Cosmic strings, hypothetical defects in spacetime, also emerge from the mathematics. Not all such solutions are realized in nature, but their existence in the equations shows the range of possibilities. Gravastars belong to this family, mathematically consistent, physically motivated, but awaiting observational confirmation. Another connection to relativity comes from the cosmological constant. As mentioned earlier, Einstein introduced it to allow a static universe, abandoned it, and then saw it return with the discovery of cosmic acceleration. In gravastars, the cosmological constant plays a local role. The vacuum energy inside the gravastar acts like a localized cosmological constant, altering space-time in the interior. This use of relativity's flexibility shows again how the same theory can describe both the universe as a whole and the fate of individual stars. The comparison to black holes highlights another feature of relativity. Both black holes and gravastars are asymptotically identical. That means that far from the object, space-time looks the same in both cases. The gravitational field depends only on the total mass, not on the internal structure. This is why gravastars are so hard to distinguish observationally. Relativity allows both, but hides their differences from distant observers. Only near the boundary does the difference become apparent. Relativity also predicts how objects influence time. Near a black hole, time slows dramatically relative to distant observers. Near a gravastar, the same would happen, because the exterior solution is the same. This slowing of time, or gravitational time dilation, is one of the most counterintuitive but well-tested predictions of relativity. Astronauts orbiting near a gravastar would experience time differently from those far away, just as near a black hole. Again, relativity unifies the experiences, even while leaving open the question of the interior. The relationship between gravastars and relativity is not just about consistency, it is also about pushing the theory to its limits. Relativity has been tested in weak fields, like planetary orbits, and in strong fields, like black holes. But the interiors of collapsed stars push it into regimes where quantum effects may matter. Gravastars represent one way of exploring those regimes. By modelling vacuum energy and shells within relativity, physicists test how far the theory can go before needing modification. It is worth noting that relativity does not include quantum mechanics. It is a classical theory, describing gravity as geometry rather than as a quantum force. This gap is where singularities arise. Gravastars, by introducing vacuum energy, hint at quantum effects, but they still operate within relativity. In this sense, they are bridges, connecting the classical world of relativity with the quantum world we do not yet fully understand. They show how relativity might accommodate quantum ideas without breaking down completely. If future observations support the existence of gravastars, it would not disprove relativity. On the contrary, it would confirm the theory's richness. It would show that relativity allows not only black holes but other exotic objects depending on conditions. If no evidence for gravastars emerges, relativity remains correct, and black holes remain the default. Either way, the theory survives. What changes is our interpretation of which solutions nature prefers. This adaptability is one of the hallmarks of relativity. It does not dictate the universe but describes its possibilities. Gravastars are one possibility among many, consistent with the equations but awaiting evidence. They remind us that even in a theory as successful as relativity, there is room for creativity, speculation and discovery. And so, gravastars and general relativity are not in conflict. They are partners in the ongoing effort to understand collapse, singularities, and the limits of physics. Whether nature builds gravastars or not, the theory allows them, and by studying them, we learn more about what relativity can and cannot tell us. When physicists speak about gravastars, the conversation inevitably drifts toward the language of quantum fields. General relativity explains gravity on the largest scales, but it does not include the rules that govern the smallest. Quantum mechanics describes the behaviour of particles, fields, and energy at the microscopic level, but it does not yet include gravity. Gravastars, as theoretical objects, live right at the intersection of these two domains. They require us to think about quantum fields not just in laboratories or particle accelerators, but on cosmic scales, where they shape the very structure of collapsed stars. A quantum field is a strange idea to grasp at first. Instead of imagining particles as little billiard balls moving through empty space, quantum field theory tells us that particles are excitations of underlying fields. The electron is an excitation of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of their own fields. These fields fill space everywhere, all the time, even in regions where no particles are present. The vacuum itself is full of them, fluctuating constantly in ways that can never be entirely quiet. One of the most surprising results of quantum field theory is that even empty space has energy. This is the vacuum energy we discussed before, the baseline activity of quantum fields. It is not optional or decorative. It is built into the fabric of reality. The Casimir effect shows us this in the lab, but on cosmic scales the same principle may determine the fate of stars and galaxies. Gravastars depend on this. Their cores are modelled as regions filled with vacuum energy, stabilized by a shell. Without quantum fields, such an idea would make no sense. But the role of quantum fields goes deeper. At extreme densities, like those inside collapsing stars, the normal states of matter no longer apply. Electrons and protons combine into neutrons, forming neutron stars. At higher densities, neutrons may dissolve into quarks, forming quark matter. Some theories go further, predicting new condensates, where particles merge into collective states. These possibilities are all described in the language of quantum fields. The gravastar shell, for instance, may require exotic forms of matter that arise only from quantum field interactions at unimaginable pressures. The challenge is that quantum field theory works beautifully in flat spacetime, but in curved spacetime, like that around collapsed stars, it becomes harder to use. Fields behave differently when space itself is bent, stretched, or compressed. Gravastars push us to consider quantum fields in curved spacetime, something we can only partially handle with current mathematics. Hawking radiation is an example of what happens when quantum fields are considered near black holes. It predicts that black holes slowly emit thermal radiation due to quantum fluctuations at the horizon. For gravastars, a similar consideration might reveal how their shells and cores interact with fields, perhaps leading to unique emissions. Thinking about quantum fields on cosmic scales also highlights one of the biggest gaps in modern physics. We do not have a complete theory of quantum gravity. General relativity and quantum field theory are our two most successful frameworks, yet they remain separate. Singularities appear in relativity because it ignores quantum effects. In gravastars, the introduction of vacuum energy hints at quantum input, but it is still not a full merger of the theories. Gravastars may therefore be stepping stones, objects that show us how quantum fields and gravity could coexist in extreme conditions. Consider again the cosmological constant problem. Quantum field theory predicts an enormous amount of vacuum energy, far more than observed. If gravastars use vacuum energy in their cores, then the properties of quantum fields at high curvature might differ from our expectations. Perhaps the energy density adjusts itself in ways we do not yet understand, allowing stability without overwhelming collapse. If this is true, then studying gravastars could help resolve the mismatch between theory and observation. They could serve as natural laboratories where quantum fields reveal their true behavior. Another way quantum fields matter for gravastars is through phase transitions. Just as water changes state when heated or cooled, quantum fields can shift into new configurations under extreme conditions. The early universe, for example, went through several such transitions as it expanded and cooled, changing the behavior of matter and forces. A collapsing star might undergo a similar transition, with its interior shifting into a vacuum-dominated state. The gravastar model assumes such a transition, where ordinary matter gives way to vacuum energy. Understanding this requires quantum field theory not at the scale of atoms, but at the scale of stars. On cosmic scales, quantum fields also produce fluctuations that seed structure in the universe. In the inflationary model of cosmology, quantum fluctuations during the universe's earliest moments were stretched to astronomical sizes, providing the seeds for galaxies and clusters. If quantum fields can shape the entire universe, it is not unreasonable to think they can shape individual collapsed stars. Gravastars become part of this pattern, showing how quantum effects, usually confined to the microscopic, can dominate at the macroscopic and cosmic. The role of quantum fields in gravastars also raises questions about entropy and information. In quantum theory, information is preserved, even if it seems hidden. Black holes challenge this principle, because they seem to erase information behind horizons. Gravastars, with shells and vacuum cores, may allow quantum fields to interact differently, preserving information in ways black holes cannot. If so, they provide a link between quantum mechanics and gravity, showing that information remains safe even under collapse. From a practical standpoint, testing these ideas is difficult. Quantum fields on cosmic scales cannot be recreated in the lab, but we can look for indirect signs, gravitational wave echoes, unusual emissions from accretion disks, or deviations in the timing of signals could all reflect quantum field behavior inside gravastars. If such signals are detected, they would not only support the gravastar model, but also teach us about quantum fields in curved spacetime. It is worth remembering that many discoveries in physics began as explorations of how quantum and classical ideas meet. The photoelectric effect revealed the quantum nature of light. Superconductivity revealed collective quantum states. Gravastars may reveal how quantum fields behave under gravity so strong that spacetime itself bends inward. They are not just exotic objects, but potential guides toward a unified theory. The idea that quantum fields, normally invisible to us, could shape stars and galaxies is humbling. It reminds us that the universe operates on principles that connect the smallest scales to the largest. The same fluctuations that once seeded galaxies may now stabilize gravastar cores. The same vacuum energy that drives cosmic expansion may prevent stellar collapse. Quantum fields are everywhere, from atoms to horizons, binding the cosmos with unseen threads. Gravastars simply highlight their role in one of the most extreme forms possible. As we move forward, the presence of quantum fields at cosmic scales reminds us that the boundaries between disciplines are artificial. Particle physics, cosmology, and astrophysics are not separate worlds, but parts of a single story. Gravastars live where those parts meet, where quantum fields and general relativity intertwine. Whether they exist or not, they embody the unity of physics, showing that the smallest and the largest cannot be separated. To understand one, we must understand the other. For most of history, gravity was invisible in every sense. We could feel its pull, watch its effects in falling apples and orbiting planets. But the idea that gravity could ripple through space itself was something no one could measure. Einstein predicted those ripples, gravitational waves, as a consequence of general relativity in 1916. They would travel at the speed of a light, stretching and squeezing space-time as they passed, carrying energy away from violent cosmic events. Yet for a century, they remained only theoretical, too faint to detect with the instruments of the time. That changed in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded the signal of two black holes colliding more than 1 billion light-years away. It was a faint shiver in the fabric of space, altering the lengths of laser arms by less than 1,000th of the width of a proton. But it was unmistakable. Humanity had heard the universe for the first time, not in light, but in vibrations of space-time itself. This discovery opened a new era in astronomy, one where we could listen to cosmic events rather than only see them. For the study of gravastars, gravitational waves are especially important. From a distance, gravastars look almost identical to black holes. Their gravitational fields are the same, their shadows against surrounding gas nearly indistinguishable. But when they collide, the details of their internal structure matter. The waves they produce carry information not only about their mass and spin, but also about what happens at their boundaries. If gravastars are real, their mergers might produce signals that differ subtly from black hole mergers, providing one of the only ways to tell them apart. The basic pattern of a gravitational wave from a merger has 3 stages. First, there is the inspiral, as two massive objects orbit each other, drawing closer as they radiate energy in gravitational waves. The frequency and amplitude of the waves increase as the objects spiral inward. Then comes the merger, the moment of collision, when the signal reaches its peak. Finally, there is the ring down, when the merged object settles into its final state, radiating away distortions until it reaches equilibrium. For black holes, the ring down has a very specific form, dictated by the properties of the horizon. For gravastars, the absence of a true horizon changes this story. Instead of absorbing all disturbances perfectly, a gravastar's shell might reflect some of the gravitational waves. These reflections could produce echoes, faint signals arriving after the main ring down. The idea is that waves bounce between the shell and the exterior, leaking out gradually. Detecting such echoes would be difficult, because they would be weak compared to the main signal, but they would be a telltale sign of a physical surface rather than a horizon. Several groups of physicists have searched the LIGO and Virgo data for such echoes. Some have reported tentative hints, though none have been confirmed. The debate continues, but the possibility itself is a powerful motivation. Beyond echoes, there are other potential differences. The way the shell vibrates when struck by the collision might produce unique oscillations. The distribution of energy in the waves might differ slightly, reflecting the internal structure. These differences would be subtle, requiring highly precise instruments to detect. But the more gravitational wave observatories we build, and the more sensitive they become, the closer we come to being able to distinguish these possibilities. The study of gravitational waves also brings in the idea of multipolar structure. Black holes are described entirely by mass, spin, and charge. Gravastars with shells and vacuum cores might have slightly different multipole moments, meaning their gravitational fields have different fine structures. These differences would show up in the inspiral phase of a merger, altering the way the frequency evolves. By comparing the observed waveforms with theoretical predictions, physicists can test whether the objects are truly black holes or something else. So far, the data matches black holes well, but the uncertainties leave room for alternatives. Another way gravitational waves could reveal gravastars is through events involving neutron stars. When neutron stars merge, the outcome can be a black hole, but it could also be a gravastar if the conditions allow. The waves from such an event might differ in ways that reflect the formation of a shell and vacuum core. If we detect such a merger and see anomalies in the signal, it could point toward the birth of a gravastar. These are rare events, but as detectors operate for longer, the chances of catching them increase. Gravitational wave astronomy is still young. LIGO, Virgo, and now CAGRA have only been running for a few years, and already they have transformed astrophysics. Future detectors, like the space-based LISA observatory, will extend our reach to lower frequencies, probing supermassive black hole mergers. If gravastars exist on galactic scales, LISA might be the instrument to reveal them. Its sensitivity will be so great that even faint echoes or deviations in the inspiral could become detectable. The future of this field is one where alternatives to black holes can finally be tested directly. The importance of gravitational waves for gravastars goes beyond just evidence. They also remind us how interconnected physics is. Gravitational waves are pure general relativity, ripples in spacetime curvature. But to interpret them in terms of gravastars, we must consider quantum fields, vacuum energy, and exotic matter. Each detection becomes not just a confirmation of relativity, but a probe into the unknown. Gravastars, if they exist, would make themselves known not through light, but through these vibrations, whispers in the fabric of reality. It is remarkable to think that the same instruments capable of detecting shifts, smaller than a proton's width on Earth, can tell us about objects billions of light-years away. It shows the precision of science, but also the patience of nature. Gravastars, if they are real, will not reveal themselves easily. They mimic black holes too well in light. But in waves, in the way they merge and settle, their differences might emerge. That is why gravitational wave astronomy is central to this search. The echoes, the oscillations, the subtle deviations, all are possibilities. None have been confirmed yet, and perhaps none will be. It is possible that black holes are exactly as relativity describes, and that gravastars are only mathematical curiosities. But until the data rules them out, the search remains open. Each new detection adds to the picture, sharpening our understanding of what collapse produces. Gravitational waves are more than just signals. They are windows into regions of the universe that light cannot reach. They bypass the opacity of plasma, the shadows of horizons, the distortions of gas. They carry pure information about mass, energy, and motion. In that information lies the chance to answer questions about gravastars, black holes, and the fate of collapsed matter. They are the evidence we have been waiting for, the language the universe uses to tell us what happens when gravity wins. Gravitational waves stand as both tools and mysteries. They confirm the reality of black holes, but they also leave open the possibility of gravastars. They give us the means to test, to compare, and to discover. Whether echoes are found or not, whether deviations appear or not, the search itself deepens our understanding. Light has always been our primary tool for studying the universe. Every star we see, every galaxy photographed by telescopes, Every nebula and supernova has reached us through photons that travelled across immense distances. Light tells us about temperature, motion, chemical composition, and distance. Even when we cannot see directly, we use other parts of the electromagnetic spectrum, from radio waves to X-rays, to piece together the story. Gravitational waves are new and extraordinary, but light remains the most abundant messenger. If graver stars exist, they will leave their marks not only in waves, but also in how they interact with light. The first way to consider this is through accretion. Matter falling into a compact object does not usually plunge directly inward. Instead, it forms a disk, spiralling in while heating up from friction and compression. These accretion disks glow with immense energy, often producing X-rays or even gamma rays. Around black holes, accretion disks are some of the brightest objects in the universe, responsible for quasars and active galactic nuclei. Graver stars, with their strong gravity, would form accretion disks in the same way. The difference arises at the boundary. In a black hole, matter crosses the event horizon silently, vanishing from view. In a graver star, matter strikes the shell. This collision could produce unique signatures. Instead of disappearing, matter might release additional radiation when it hits the surface. The shell might heat, glow, or emit bursts as it absorbs material. The exact details depend on the nature of the shell, which remains speculative, but the principle is clear. A physical surface interacts with matter differently than an event horizon. Observing such differences would be difficult, because accretion disks are chaotic environments with many competing processes. But in principle, if we study emissions carefully enough, we might detect anomalies that point to graver stars. Another signal lies in shadows. The Event Horizon Telescope captured the first image of a black hole shadow in 2019, showing the dark silhouette of the supermassive object at the centre of galaxy M87. This shadow arises not from the horizon itself, but from the bending of light around the object, creating a bright ring with a central darkness. A graver star would produce almost the same shadow, because its external gravitational field is identical to a black hole's. But some subtle differences could exist. If light reflects from the shell rather than vanishing, the interior of the shadow might not be perfectly dark. Faint emissions or distortions could appear, offering a clue. Detecting such differences requires extremely precise imaging, but as instruments improve, this may become possible. Silence is another signal. Black holes are silent in the sense that once matter crosses the horizon, it makes no sound or light we can detect. Graver stars with their shells might not be so quiet. Collisions with the shell could produce vibrations, oscillations that radiate as electromagnetic or gravitational signals. This lack of silence could distinguish them, though again, the differences would be subtle and easily hidden by the noise of astrophysical processes. Astrophysical signals also extend to jets. Many black holes produce powerful jets of particles, launched from the regions around their accretion disks. These jets travel at nearly the speed of light, extending thousands or even millions of light years. The mechanisms behind jets are not fully understood, but they involve magnetic fields and the rotation of the black hole. If graver stars exist, they too could produce jets, but the presence of a shell might change the details. The efficiency of jet formation, the structure of the outflows, or the variability of emissions might differ. Observing such differences is challenging, but as with other signals, careful study could reveal clues. Timing offers another possible distinction. Pulsars, for example, are neutron stars that emit beams of radiation with precise regularity. If graver stars have shells that vibrate or oscillate, they might produce signals with characteristic timing patterns. Bursts of radiation could occur when matter impacts the shell, producing quasi-periodic oscillations. These timing features might stand out in X-ray data or radio observations. They would not prove graver stars outright, but could suggest that something other than a black hole is at play. Astrophysical silence is also about what we do not see. If graver stars exist, some of the objects we currently classify as black holes might behave slightly differently. Perhaps they are less efficient at swallowing matter, leaving behind faint emissions. Perhaps their shadows are not as dark as predicted. Perhaps their mergers produce echoes in waves. The absence of perfect silence, small anomalies in data, could be the first hints. Physicists must be careful though, because astrophysical environments are complex and anomalies can arise from many causes. Still, silence broken in unexpected ways could be a signature. Light also carries polarization, the orientation of its waves. Around black holes, polarization patterns reveal the structure of magnetic fields near the horizon. Gravastars with shells might alter these patterns slightly. If matter strikes the surface, the resulting radiation could have different polarization properties than matter vanishing past a horizon. Observations of polarized light from quasars and active galactic nuclei may eventually test this idea. We should also consider transient signals, short-lived events like gamma-ray bursts. These bursts occur when massive stars collapse or neutron stars merge, producing intense flashes of radiation. If gravastars form in such events, the signals might differ from those expected from black holes. For instance, the presence of a shell could produce secondary bursts or unusual afterglows. Detecting such differences requires precise timing and broad coverage, but modern observatories are improving rapidly. Astrophysical signals are often messy, layered with noise and uncertainty. But this messiness is also opportunity. Gravastars may not announce themselves with clear dramatic signatures. Instead, they may whisper through slight deviations, subtle anomalies, or unexpected silences. The challenge is to interpret these whispers without leaping to conclusions. Many anomalies have turned out to be calibration errors, background noise, or misunderstood processes. But some may one day reveal new physics. It is humbling to realize how much of our understanding depends on interpreting signals that have traveled across millions or billions of light years. A photon emitted near a gravastar's shell may journey across the cosmos, bent by gravity, scattered by dust, and finally captured by a detector on Earth. In that photon's properties lies the story of its origin. Decoding that story is the task of astrophysics, and gravastars add a new layer of complexity to the task. As instruments grow more precise, from radio arrays to X-ray telescopes, we will gather more data. The Event Horizon Telescope will sharpen its images. Future X-ray observatories will capture finer details of accretion disks. Gravitational wave detectors will hear faint echoes. Together, these signals may one day confirm or rule out gravastars. Until then, we listen not only to light but also to silence, knowing that sometimes the absence of a signal speaks louder than its presence. Astrophysical signals, whether in photons, jets, shadows, or silences, remind us that the universe is not only vast but subtle. Black holes and gravastars may be nearly indistinguishable, but nearly is not the same as entirely. Somewhere in the faint details, in the quiet after a burst, in the brightness of a ring, in the timing of oscillations lies the truth. Our task is to watch, to listen, and to interpret with care. Gravastars may reveal themselves not with fireworks, but with quiet deviations, with the smallest differences between light, shadow, and silence. When people hear about black holes, what often captures the imagination is their destructive reputation. They are portrayed as cosmic vacuum cleaners, devouring anything in their reach, tearing stars apart, swallowing light itself. Gravastars, if they exist, belong to the same family of extreme objects, and their potential for destruction is no less extraordinary. To understand this destructive power, though, we need to think carefully about energy, because in physics, destruction is almost always a matter of how energy is released, transformed, or unleashed. Consider first the collapse that could give rise to a gravastar. When a massive star dies, the gravitational energy released in its collapse is staggering. In a supernova, just a fraction of that energy powers an explosion so bright it can outshine a galaxy. Most of the energy, however, goes into neutrinos, nearly massless particles that stream out in enormous numbers. The final remnant, whether a neutron star, black hole or grav star, represents the endpoint of this energy transformation. In the case of a grav star, the formation of a vacuum core and ultra-dense shell may involve a phase transition in spacetime itself. Phase transitions release energy, and on cosmic scales the release could be immense. If the shell forms suddenly, the energy emitted could rival or exceed that of a traditional supernova. The violent shift from ordinary matter to vacuum energy might produce bursts of radiation, gravitational waves, or particle emissions unlike anything we have yet observed. This possibility ties into gamma-ray bursts, which are some of the most energetic events in the universe. Some physicists have speculated that unusual bursts might hint at exotic processes, including the birth of graver stars. Even if such connections remain speculative, the principle holds. Whenever space-time itself undergoes a transition, the energy released could be catastrophic. Once formed, graver stars would continue to demonstrate destructive potential through their interactions with surrounding matter. Like black holes, their gravitational pull would dominate their environments. Any star or gas cloud that strayed too close could be shredded, its matter heating up and radiating energy as it fell inward. The difference is that instead of vanishing past a horizon, the matter would slam into the shell. This collision could produce flashes of radiation even more violent than the accretion processes around black holes. In this sense, graver stars might not only rival black holes in their destructiveness, but even surpass them in how violently they process in falling matter. The energy released from these collisions depends on the properties of the shell. If the shell is perfectly absorbing, the energy would convert to heat, perhaps radiating outward over time. If the shell reflects or partially absorbs matter, the interactions could produce bursts or oscillations. Either way, the energy unleashed would be vast, enough to strip atmospheres from nearby stars or sterilize planets in the region. To any life unlucky enough to exist nearby, the presence of a graver star would be catastrophic. Another dimension of destructive potential comes from mergers. When two black holes collide, they release gravitational waves carrying more energy than all the stars in the universe combined during those moments. If two graver stars collide, the process could be even more dramatic. Their shells would smash together, their vacuum cores would interact, and the balance that stabilizes them might break down. The resulting release of energy could exceed that of black hole mergers, producing signals we have yet to detect. These collisions could shake galaxies, sending ripples through space-time that travel across the cosmos. Even on cosmic timescales, graver stars could be destructive in quieter but equally profound ways. Their immense gravity could disrupt stellar systems, flinging planets into interstellar space. They could alter the dynamics of star clusters or influence galactic centers. Just as supermassive black holes shape the evolution of galaxies, supermassive graver stars could do the same. Their influence would be both creative and destructive, regulating star formation while also consuming or sterilizing regions around them. One of the most destructive aspects of graver stars is not what they do directly, but what they imply. If they exist, then space-time itself is capable of shifting into new states under collapse. That means the universe contains hidden reservoirs of energy, locked in the structure of the vacuum, waiting to be unleashed under the right conditions. The destructive potential of graver stars is therefore also a reminder of how little we understand about the vacuum. If it can stabilize stars, it can also, under other circumstances, destabilize them, releasing catastrophic amounts of energy. There is also the possibility of instability. If graver stars are not perfectly stable, they might collapse after long periods, releasing their stored energy in sudden bursts. A collapsing graver star could produce radiation unlike any black hole, as its shell fails and its vacuum core changes state. Such an event would be among the most destructive imaginable, a delayed explosion that could rival the energy of the brightest quasars. The universe may contain such ticking time bombs, though we have not yet identified them. destructive potential must also be considered in the context of scale. A stellar mass grav star would be catastrophic in its local region, but a supermassive grav star at a galactic center would influence millions of stars. Its accretion processes could generate radiation bright enough to outshine the galaxy. Its mergers could release energies that reshape entire regions of spacetime. If grav stars can exist on supermassive scales, then their destructive reach could span entire galaxies. But perhaps the most profound form of destruction associated with grav stars is conceptual. Black holes already force us to confront paradoxes, infinities, and the possible breakdown of physics. Grav stars, by avoiding singularities and horizons, change the narrative. They tell us that what we thought was the ultimate form of destruction, the crushing of matter to infinite density, may not exist. Instead, destruction is replaced by transformation, where energy is not erased but redistributed. This redefinition of destruction challenges our deepest assumptions about the cosmos. From the perspective of physics, destruction is always about energy changing form. Stars explode because nuclear fuel runs out and gravity wins, releasing energy and collapse. Planets are torn apart by tides, their material converted into heat and radiation. Grav stars represent destruction on another level, where even space-time undergoes transitions that release energy. They show us that destruction is not an endpoint but a process, one that reshapes matter and energy in ways we're only beginning to imagine. It is tempting to imagine grav stars as more dangerous than black holes, as if nature invented an even harsher predator. But danger is a human perspective. For the universe, there is no good or bad, only processes. Grav stars, if real, would simply be another way matter and energy evolve. Their destructive potential is immense, but so is their creative role, shaping galaxies, producing radiation, and perhaps preserving information that black holes would lose. They are both destroyers and archivists, cosmic furnaces that burn not with fire but with the hidden energy of the vacuum. And so, the destructive potential of grav stars is not limited to tearing stars apart or unleashing bursts of energy. It is also about what they reveal, that the universe is far more violent, far more creative, and far more surprising than we imagined. Destruction, in this context, is not the end but the means by which new structures arise, by which energy takes new forms, and by which physics exposes its hidden depths. Grav stars, if they exist, embody this paradox. They are destructive, but their destruction is the key to stability, balance, and perhaps even understanding. When we think about destructive things in the cosmos, we usually place them in local contexts. A supernova destroys the star that explodes and any planets unlucky enough to orbit it. A gamma ray burst sterilizes anything within its beam for thousands of light years. A black hole consumes what falls too close, but beyond its reach, the galaxy continues as before. These are catastrophic events, but they are regional, not universal. The universe as a whole continues unaffected. Grav stars, however, raise the question of whether destruction could operate on a larger scale. If their cores are made of vacuum energy, if they represent phase transitions in spacetime itself, could they in some way threaten the structure of the universe? To begin, we have to think about what threat means in a cosmic sense. The universe is not fragile in the way we think of living systems as fragile. Stars die, galaxies collide, black holes merge, and yet the large-scale structure persists. Gravity continues to shape matter into clusters, voids, and filaments. Expansion continues. The laws of physics remain. For something to threaten the universe itself, it would have to undermine the very fabric of space-time or alter the constants that allow it to exist as it does. Grav stars, in their reliance on vacuum energy, bring us close to such considerations. Vacuum energy is not just a local property. In cosmology, it is the dominant component of the universe, driving accelerated expansion. If the vacuum energy inside a grav star behaves differently from the cosmic average, then the question arises, could it spread? Could the formation of a grav star trigger a chain reaction, altering the vacuum state of the universe. This is not idle speculation. Some theories of physics suggest that our universe may be in a metastable vacuum state, one that could, in principle, decay to a lower energy state. If such a transition were triggered, the consequences would be catastrophic, altering the laws of physics instantly and reshaping the universe beyond recognition. Does this mean graver stars could be seeds of such destruction? The answer depends on how vacuum energy behaves. If the vacuum inside a graver star is the same as the cosmic vacuum, then there is no danger. It is simply a local manifestation of the same energy that already fills space. If it is a different vacuum state, then the possibility arises that under the right conditions it could destabilize. This is the kind of speculative physics that reminds us how much we do not know about the vacuum. Graver stars serve as thought experiments, prompting us to ask these questions even if the real danger is remote. Another way graver stars could be seen as threats is in their gravitational influence. If supermassive graver stars exist at galactic centers, they would shape galaxies just as supermassive black holes do. Their gravity would bind stars, regulate star formation, and drive cosmic evolution. This is not a threat in the sense of destruction, but it is a way they influence structure. If graver stars were somehow more efficient at releasing energy than black holes, their influence could be even greater, potentially altering the growth of galaxies or the distribution of matter on large scales. But we should be careful. The universe is robust. It has endured countless collapses, explosions, and mergers. If graver stars exist, they are part of that robustness, not enemies of it. They are not cracks in the structure, but alternative outcomes within it. The real threat they pose is not to the universe's survival, but to our understanding of it. They challenge the notion that black holes are the ultimate fate of collapse. They challenge the assumption that singularities are inevitable. They threaten the neatness of our models by offering a different path, one that forces us to reconsider the balance between relativity and quantum mechanics. Yet there remains the speculative possibility that graver stars could destabilize more than our theories. If their vacuum cores are exotic enough, if they represent different states of space-time, then their collisions or instabilities could, in principle, unleash energies on scales that dwarf even supernovae. Could such releases ripple outward, altering space-time beyond their immediate surroundings? Possibly, though current physics gives no evidence that this happens. If it did, the universe we observe would look very different. Another dimension of threat comes from information. Black holes threaten the principle of information conservation, creating paradoxes that strike at the heart of physics. Graver stars, by avoiding horizons, might preserve information. In that sense, they are less threatening than black holes. But if they store information in their shells, what happens when those shells fail? Could the sudden release of information itself destabilize systems? Again, these are speculative questions, but they illustrate how graver stars push us to think about the universe in unfamiliar ways. For life, graver stars would certainly be threats if they existed nearby. Their radiation, their gravitational influence, their potential for bursts of energy, all would be devastating. But on cosmic scales, they are likely no more threatening than black holes. The universe has room for such objects. Its structure arises from balance, gravity pulling matter into filaments, expansion driving it apart, dark energy shaping the future. Graver stars would be part of this balance, not destroyers of it. What they do threaten is our sense of finality. For decades, black holes have been the ultimate symbol of cosmic endings. Matter falls in, horizons trap it, singularities consume it. Graver stars suggest that endings may not be so absolute. Collapse may halt, balance may emerge, destruction may give way to transformation. In this sense, graver stars threaten not the universe, but our narratives about it. They replace finality with complexity, singularities with shells, and horizons with boundaries. If we ask whether graver stars threaten the structure of the universe, the answer is almost certainly no in the physical sense. They do not destabilize space-time on large scales. They do not spread like contagions. They do not unravel galaxies or cosmic expansion. But they do represent the possibility of new physics, and that is a kind of threat to complacency. They remind us that what we call the structure of the universe is not just matter and energy, but also the frameworks we use to describe them. Gravastars threaten to rewrite those frameworks, and so, in the grand scheme, gravastars are not enemies of the cosmos but provocations for thought. They force us to confront the vacuum, to question singularities, to test relativity and quantum mechanics against each other. Their threat is intellectual, not existential. The universe continues, robust and indifferent, while we wrestle with the models we use to explain it. Gravastars may never be observed, or they may turn out to be common. Either way, they enrich our understanding of what destruction means, not as an end, but as a transformation that preserves the fabric of reality. Every time physics has seemed complete, every time we thought the universe was finally understood, something new has arrived to remind us of the gaps in our knowledge. Gravastars are one of those reminders. They are not confirmed, not observed directly, and yet they sit at the crossroads of some of the deepest mysteries in science. Their very possibility highlights what physics still does not know. To close this exploration, it helps to step back and look at these open questions, not as failures, but as signposts pointing the way forward. One of the most glaring unknowns is the nature of singularities. General relativity predicts them, but most physicists believe they cannot exist in reality. Infinite density and curvature are not physical states, but signs that the theory is incomplete. Yet without a complete theory of quantum gravity, we cannot prove this. Gravastars represent one attempt to avoid singularities, but until we know how gravity and quantum mechanics merge, we cannot say for sure what happens at the end of collapse. The singularity problem remains unsolved, the first great mystery still waiting for resolution. Closely tied to this is the information paradox. Black holes seem to erase information, violating the principle of unitarity in quantum mechanics. Hawking radiation complicates the picture further, raising questions about what happens to the details of the matter that falls in. Gravastars offer one possible escape, preserving information on their shells rather than losing it beyond horizons. But without observational evidence, this remains speculation. What physics still does not know is whether information is truly safe in the universe or whether collapse represents a fundamental break in predictability. Another unknown is the nature of vacuum energy. We know it exists because it shapes the expansion of the universe. We know it has negative pressure, but we do not know why its magnitude is so small compared to the predictions of quantum field theory. The mismatch is staggering, the worst theoretical prediction ever made. Gravastars depend on vacuum energy in their cores, but until we understand the vacuum itself, we cannot say how realistic this is. What physics still does not know is whether the vacuum is stable, whether it can change state, and whether gravastars can form from it. The properties of ultra-dense matter also remain uncertain. Neutron stars push matter to extremes we cannot reproduce in laboratories, but gravastar shells go further still. Quark matter, strange matter, condensates, or other exotic states may exist, but their equations of state are unknown. The physics of the shell, its stability, and its interactions within falling matter all depend on this. Until we understand matter under such conditions, gravastar models remain incomplete. What physics still does not know is how matter behaves when pushed beyond all familiar limits. Gravitational waves have opened new windows, but they also remind us of the limits of detection. Echoes, deviations, and anomalies could reveal gravastars, but so far the signals are consistent with black holes. That may be because black holes are indeed correct, or it may be because our instruments are not yet sensitive enough. What physics still does not know is whether gravitational waves will eventually show us differences, or whether gravastars will remain hidden forever in the noise. Astrophysical signals raise similar uncertainties. Shadows, emissions, jets, and bursts all look consistent with black holes, but the possibility of subtle differences remains. Our current data is limited, and the complexity of astrophysical environments makes interpretation difficult. Graver stars may reveal themselves through light, shadow, or silence, but we may not yet have the tools to distinguish them. What physics still does not know is whether the universe is showing us graver stars already, disguised as black holes, and whether we are simply missing the clues. On an even broader level, the question of stability remains unresolved. Could graver stars last for billions of years, shaping galaxies and merging in detectable ways? Or are they transient, collapsing quickly into black holes? Without knowing the details of their formation and structure, we cannot answer this. What physics still does not know is whether graver stars are real, lasting objects, or fleeting possibilities. These unknowns point toward the deepest mystery of all, the unification of relativity and quantum mechanics. Relativity governs the large, quantum mechanics the small, and they work perfectly in their own domains. But at the extremes, inside black holes, at the Big Bang, and in objects like graver stars, the two must meet. We still lack a full theory that unites them. String theory, loop quantum gravity, and other approaches exist, but none have been confirmed. Graver stars highlight the urgency of this search because they live at the intersection. What physics still does not know is how the universe truly works when the rules of both gravity and quantum fields apply equally. It is tempting to think of these gaps as failures, but they are not. They are invitations. They are reminders that physics is a work in progress, that the universe always has more to reveal. Every unanswered question is a frontier, every paradox a doorway. Graver stars embody this spirit. Whether they exist or not, they point to the questions we must answer. What is the vacuum? What happens at singularities? How does information survive? And how do gravity and quantum mechanics become one? In the end, what physics still does not know is vast. But this is not discouraging. It is the essence of science. The mysteries of graver stars are not barriers but guides, leading us toward new theories, new instruments, and new ways of thinking. The universe has always been larger, stranger, and more surprising than we expected. Graver stars are part of that surprise, whether as real objects or as ideas that push us forward. And so, as we let the mind settle, the story of graver stars remains unfinished. They may exist, hidden among the black holes we think we know. They may not, serving only as stepping stones toward a deeper understanding. Either way, they remind us of what physics still doesn't know, and of why that ignorance is not weakness but strength. It is the reason to keep listening, keep watching, and keep asking questions, knowing that the answers are still out there, waiting in the silence of the universe. Thank you for drifting with me through this journey, one that has taken us from the life and death of stars to the strange possibility of graver stars. Together we have explored the physics of collapse, the mystery of vacuum energy, the role of shells and pressure, and the delicate balance that might prevent singularities. We have compared graver stars to black holes, listened for their possible echoes in gravitational waves, searched for their fingerprints in light and shadow, and considered both their destructive potential and the unanswered questions they bring. Perhaps what lingers most is not certainty but openness. The universe has not yet told us whether graver stars are real. But in asking about them, in following the threads of physics that lead toward them, we are reminded that the cosmos is not exhausted by our current understanding. There are still mysteries, still gaps, still puzzles large enough to keep us wondering. That wonder is the very heart of science. And so, wherever you are listening from, know that you are sharing in a tradition as old as humanity itself, the desire to look up, to listen, to ask questions about the sky. The answers are never final, but the questions themselves are what connect us to the universe. Whether graver stars exist or not, they have already given us something valuable, the chance to imagine, to learn, and to rest in the comfort that there is always more to discover. If this journey has soothed you, if it has given you a sense of calm or curiosity, I invite you to stay with this space. to like and subscribe so you can return whenever you want, to drift again into the quiet of science. Now let the mind settle. Let the last traces of curiosity soften into rest. The universe continues its vast work, stars are born and die, galaxies evolve, and perhaps graver stars wait silently in the dark. For you, though, the journey can pause here, in stillness, with nothing more required than to breathe, to rest, and to dream beneath the same stars we have been thinking about all along.